Did you know stars are actually alive? Not like you or me, but in a way that's way more mysterious. They're born, they live for billions of years, and then they die in explosions so huge they reshape entire galaxies. But what happens right before that death? NASA scientists have discovered secrets hidden in starlight that'll change everything you thought you knew about the night sky. Today, we're diving into the cosmic dance of stars. I'm breaking down what NASA researchers have uncovered about the final moments before a star dies. This isn't just science. It's a story of creation, destruction, and the stuff that makes up you. Stick around, because what stars hide before death is wilder than any sci-fi movie. Here's the thing. Stars look peaceful, twinkling above us, right? But they're actually ticking time bombs. For most of their lives, they're calm, balancing forces like a cosmic tightrope walker. Gravity tries to crush them, while nuclear explosions inside push back. But when that balance breaks, chaos. And here's the puzzle. Stars don't just stop working. They go through secret changes we can't see with the naked eye, changes that determine whether they fade quietly or take half the universe with them. NASA's been tracking these invisible signals, and what they found? It's like solving a murder mystery written in light. So, what is a star? Imagine a giant ball of gas, mostly hydrogen and helium, so massive its own gravity squeezes it until it gets hot enough to start nuclear fusion. That's when it lights up. Our sun? It's been doing this for 4.6 billion years. But stars aren't forever. They're like cosmic batteries. Once their fuel runs low, things get weird. First, let's talk size. Not all stars die the same way. Small stars, like red dwarfs, burn slow and steady. They can live for trillions of years, longer than the universe has existed. But bigger stars, they're drama queens. They live fast, die young, and go out with a bang. Think of it like this. A small star is a candle, while a big star is a firework. Both run out of fuel, but one just flickers out, and the other explodes. Now here's where NASA's work comes in. Using telescopes like Hubble and James Webb, scientists look for clues in starlight. When a star starts dying, it changes color and brightness. It might swell into a red giant, swallowing planets nearby, or it could start pulsing, like a heartbeat growing irregular. These are warning signs, but the real secrets are in the elements stars create. See, stars are element factories. They fuse hydrogen into helium, then helium into carbon, oxygen, and heavier stuff. But when they're about to die, they start making iron. Iron is like poison to a star. It doesn't release energy when fused. It absorbs it. So when a star's core fills with iron, it's game over. The core collapses in seconds. Imagine something the size of Earth shrinking to the size of a city. That collapse triggers a supernova, an explosion brighter than entire galaxies. But NASA's found something even wilder. Before that final collapse, stars do something bizarre. They shed their outer layers like snakes shedding skin. These layers drift into space, forming beautiful clouds called nebula. But inside those clouds, hidden elements, gold, silver, uranium, stuff that doesn't form anywhere else. The gold in your jewelry, it came from a dying star, and NASA's mapped how these elements spread, seeding the universe with the building blocks of planets, even life. There's more. Stars also spin and wobble as they die. Their magnetic fields go haywire, creating solar flares that could fry electronics on Earth if they happened close enough. Scientists track these wobbles using light patterns. It's like listening to a star's heartbeat through a stethoscope made of telescopes. The faster the wobble, the closer to death. And get this, stars don't die alone. They often have companion stars. When one starts dying, it can steal material from its neighbor, speeding up its own death, or it might trigger the companion's death too. It's a cosmic domino effect. NASA's spotted pairs of stars where one's already dead, a neutron star or black hole, and the other's about to explode. These binary systems are like ticking time bombs. But the biggest secret NASA's uncovered: stars know they're dying. Not in a conscious way, but physically. They release neutrinos, ghostly particles that pass through almost anything, hours before the supernova. These neutrinos are like a star's final scream. Scientists can detect them with underground sensors. So when a star's about to blow, we get a warning. It's the universe's ultimate spoiler alert. And here's the mind-blowing part. Those neutrinos travel at light speed, but the star's visible explosion lags behind. So we see the neutrino signal before we see the star explode. That means we're watching death in reverse. So stars aren't just balls of gas. They're cosmic artists, creating elements and painting nebulae. They're time bombs, with secrets hidden in their light and wobbles. And when they die, they don't just disappear. They give birth to new stars, planets, maybe even life. NASA's work shows us that death in space isn't an end, it's a transformation. Picture this, a dark, cold cloud in space, invisible to your eyes. But inside, a star is being born right now. NASA scientists have watched this cosmic pregnancy unfold, and what they've found will make you see the night sky completely differently. Today, we're diving into how stars come to life. I'm breaking down NASA's discoveries about star birth, from ghostly clouds to nuclear fire. This isn't just astronomy. It's the story of how everything around us, including you, began. Stick around, because the birth of a star is wilder than any creation myth. Here's the thing. Space is mostly empty. So how do stars, these massive blazing objects, just appear out of nothing? That's the puzzle NASA's been solving. See, stars don't just pop into existence. They need specific conditions, like a cosmic recipe with ingredients that are hard to mix. Gravity, gas, dust, time, they all have to line up perfectly. If one thing goes wrong, no star. And here's the kicker. We can't just watch this happen in real time. Star birth takes millions of years, so scientists have to be cosmic detectives, piecing together clues from different stages of the process. It's like trying to understand human growth by only looking at babies and adults, with nothing in between. So where do stars come from? It starts with something called a nebula. Think of a nebula as a giant, cold cloud in space. Not like the clouds you see in the sky. These are made of gas and dust, mostly hydrogen and helium, but also heavier elements spat out by dying stars. These clouds are huge. Some are light years across. That's so big. If you could travel at the speed of light, it'd take you years to cross one. And they're cold, really cold, like -400 degrees Fahrenheit cold. At that temperature, gas molecules move slow, barely touching each other. But space isn't completely still. Sometimes, a nearby star explodes, sending shockwaves through space. Or maybe two galaxies collide, stirring things up. These events squeeze parts of the nebula, making some areas denser. Gravity does the rest. In these dense spots, gas and dust start clumping together. The more mass they gather, the stronger their gravity gets. It's like a snowball rolling downhill, picking up more snow as it goes. Over hundreds of thousands of years, these clumps grow into what scientists call protostars. Now, a protostar isn't a star yet. It's more like a star embryo. It's hot and glowing, but only because of gravity crushing it, not because it's generating its own energy. As it keeps pulling in more material, it spins faster and faster, like an ice skater pulling in their arms. This spinning flattens the material around it into a disk. You've probably seen pictures of Saturn's rings. It's like that, but made of gas and dust. And in the center, the protostar keeps getting hotter and denser. NASA's telescopes, like Spitzer and James Webb, have watched these protostars form. They see them glowing in infrared light, which is heat radiation we can't see with our eyes. Some protostars shoot out jets of gas from their poles, like cosmic fountains. These jets can stretch for trillions of miles. Scientists think these jets help the protostar regulate its growth, like a pressure valve releasing excess material. As the protostar keeps collapsing, its core gets hotter and hotter. We're talking millions of degrees. At these temperatures, something incredible happens. Hydrogen atoms, which normally repel each other, get squeezed so close they fuse together. This is nuclear fusion. When hydrogen atoms fuse, they form helium, and they release a tremendous amount of energy. This is the same process that powers hydrogen bombs, but in stars, it's controlled and steady. When fusion starts, it's like flipping a switch. The energy pouring out from the core pushes back against gravity. For the first time, the star stops collapsing. It reaches a balance. Gravity wants to crush it, but fusion pushes back. This balance is what makes a star stable. And when that balance is achieved, the star is officially born. It enters what's called the main sequence phase. Our sun is in this phase right now. It's been fusing hydrogen into helium for about 4.6 billion years, and will keep doing so for about 5 billion more. But not all protostars make it. Some are too small. They never get hot enough to start fusion. These become brown dwarfs, failed stars that glow dimly from leftover heat, but never truly ignite. Others are too big. They form so quickly that their radiation blows away the surrounding gas before they can gather more mass. These massive stars are rare, but live fast and die young. NASA's also found that stars don't usually form alone. They're born in clusters, like cosmic families. A single nebula can give birth to hundreds or thousands of stars at once. These sibling stars start out close together, but over time, they drift apart. Some get ejected from the cluster entirely, becoming lone wanderers in the galaxy. Others stay together, orbiting each other in pairs or groups. And here's something mind-blowing. The disks around protostars, they're where planets form. The dust and gas in these disks clump together, building planets, moons, asteroids, and comets. So when we look at a protostar, we're not just seeing a star being born, we're seeing a solar system in the making. The James Webb Telescope has actually spotted these disks around young stars, some with gaps where planets are already forming. It's like seeing a baby's first ultrasound, but for an entire solar system. But the most incredible moment NASA's captured, the instant fusion ignites. It's called hydrogen ignition, and it's like a star's first breath. Scientists can't see this directly, but they can detect the change. Before ignition, a protostar glows in infrared. After ignition, it starts shining in visible light. It's like a cosmic light bulb turning on, and when that happens, the star begins its life, releasing energy that will eventually travel across space, maybe reaching Earth millions of years later as starlight. That light? It's the same light you see when you look up at the night sky. Every star you see went through this exact process. So star birth isn't magic, it's physics. Gravity pulls gas and dust together, heat builds up, fusion ignites, and a star is born. It's a process that takes millions of years, but it's happening all over the universe right now. And every star, including our sun, started this way. NASA's work shows us that we're all made of stardust. Literally, the elements in your body were forged in stars that lived and died long before Earth existed. Did you know stars spend 90% of their lives doing the exact same thing? It's like they're stuck in cosmic autopilot. But NASA scientists have discovered this boring phase is actually hiding secrets that control how every star dies. Today, we're diving into the main sequence, the longest chapter in a star's life. I'm breaking down what NASA's learned about this seemingly stable phase and why it's the calm before the storm. Stick around, because what happens here determines whether a star fades quietly or takes the universe down with it. Here's the weird thing. Stars look peaceful during their main sequence phase. Our sun's been doing this for 4.6 billion years, and it'll keep doing it for 5 billion more. But NASA's found that beneath that steady surface, stars are actually ticking time bombs. The problem? We can't see what's happening inside. It's like watching someone's face and thinking they're fine, while internally their heart is failing. Stars are constantly balancing on a knife's edge between two forces, gravity trying to crush them, and nuclear fusion pushing back. And when that balance starts to wobble, that's when things get dangerous. So what exactly is the main sequence? Think of it as a star's adulthood. After the chaotic birth phase we talked about, Stars settle into a stable routine. They're fusing hydrogen into helium in their cores, releasing energy that makes them shine. This process is so steady that we've used it to define star types. Small stars burn slow and cool. They're red dwarfs. Medium stars like our sun are yellow. Big stars burn hot and fast. They're blue. But size isn't the only thing that matters. NASA's been studying main sequence stars using telescopes like Kepler and TESS. These space observatories watch stars for tiny dips in brightness when planets pass in front of them. But they've also found something unexpected. Stars aren't as stable as we thought. Even during their boring phase, they flicker. These aren't random twirls. They're messages from deep inside the star. Imagine a star as a boiling pot of water. On the surface, it looks calm, but underneath, bubbles are rising and bursting. Stars do the same thing. Hot plasma from their core rises to the surface, cools, and sinks back down. This process, called convection, creates sound waves that travel through the star. NASA scientists can listen to these waves using a technique called astroseismology. It's like stellar ultrasound. By measuring how the star's surface vibrates, they can map what's happening inside. And what they've found is wild. Even stars that look identical from the outside can have wildly different interiors. Some have turbulent cores, mixing material like a cosmic blender. Others have layered cores like an onion. This internal structure determines how long a star stays on the main sequence and how it'll die. Take our sun, for example. Its core is a well-organized machine. Hydrogen fuses into helium in a tight, dense center. But not all stars are so neat. Big stars have convective cores that constantly stir things up. This mixing brings fresh hydrogen into the core, letting them fuse fuel faster. That's why massive stars live fast and die young. Some only last a few million years compared to our sun's billions. But here's where it gets really interesting. NASA's discovered that stars don't fuse hydrogen the same way everywhere. In small stars like red dwarfs, hydrogen fuses through a process called the proton-proton chain. It's slow and steady. In bigger stars, they use the CNO cycle. Carbon, nitrogen, and oxygen act as catalysts to speed things up. This difference affects everything: the star's temperature, its lifespan, even what elements it creates. And elements are key. During the main sequence, stars are busy making helium, but they're also creating tiny amounts of heavier elements like carbon and nitrogen. These elements get mixed to the surface through convection. NASA's spectrographs can detect these elements in starlight, telling us what's happening inside. It's like reading a star's chemical fingerprint. But the biggest secret NASA's uncovered: stars aren't solitary. They're influenced by their neighbors. In star clusters, where hundreds of stars are born together, their gravity affects each other. Close encounters can strip material from a star's outer layers, changing its evolution. Binary stars, two stars orbiting each other, are even more dramatic. They can steal material from each other, speeding up or slowing down their main sequence phase. Some binary stars are so close they share material, creating weird hybrid stars that shouldn't exist. And then there's stellar weather. Stars have spots, flares, and superstorms, just like the sun, but on a much bigger scale. NASA's watched stars with spots so big they'd swallow Jupiter. These dark areas are cooler patches where magnetic fields get tangled. When these fields snap, they release solar flares that could fry entire solar systems if they happened close enough. But here's the thing: more active stars might actually live longer. Their magnetic fields act like a thermostat, regulating how fast they burn fuel. But the most mind-blowing discovery? NASA's found that stars remember their birth. The chemical composition of a star, what elements it was born with, determines its entire life. Stars born with more metals, astronomers call everything heavier than helium a metal, burn hotter and die faster. Metal-poor stars live longer. And here's the kicker: the first stars in the universe had almost no metals. They were massive, lived fast, and died in explosions that seeded the cosmos with the first heavy elements. Without these early deaths, there'd be no Earth, No us. NASA's telescopes have spotted these ancient, metal-poor stars, cosmic fossils that tell us how the universe began. So the main sequence isn't boring. It's a delicate balance that controls a star's destiny. Every flicker, every element, every magnetic field plays a role in how long a star lives and how it'll die. NASA's work shows us that even in stability, there's drama. The main sequence is where stars set the stage for their final act. Stars don't just die overnight. For millions of years before their final breath, they start sending secret signals. NASA scientists have cracked these cosmic warnings, and what they've found will change how you see every star in the sky. Today, we're uncovering the first whispers of stellar death. I'm breaking down how stars begin to age, changes so subtle they're invisible to the naked eye. Stick around, because NASA's discovered these early signs determine whether a star becomes a peaceful white dwarf or a universe-shattering supernova. Here's the problem. Stars look the same for billions of years. One day they're steady, the next they're dying. But NASA's found that death isn't sudden. It's a slow, hidden process. The challenge? We can't see inside stars. We can't watch their cores change or their fuel run low. So how do we know when a star is aging? It's like trying to tell when a car's engine is about to fail just by looking at its paint job. The answers are written in light, but you need to know how to read them. So what happens when a star starts aging? It all begins in the core. During the main sequence, stars fuse hydrogen into helium, but hydrogen isn't infinite. As it runs low, the core contracts under gravity's pull. This squeezing makes the core hotter and denser. Meanwhile, the outer layers expand. The star gets bigger, cooler, and redder. This is the first visible sign. The star becomes a red giant. But that's just the tip of the iceberg. NASA's Kepler Space Telescope spotted stars flickering before they turned red giants. These weren't random twirls. They were pulses, like a heartbeat growing irregular. Scientists call these stellar oscillations. As the core contracts, it creates shockwaves that ripple through the star, making its surface vibrate. By measuring these vibrations, NASA can map what's happening inside. It's like listening to a star's chest with a cosmic stethoscope. But there's more. Stars also change chemically as they age. During the main sequence, they fuse hydrogen into helium, but when hydrogen runs low, they start fusing helium into carbon. This process creates heavier elements that rise to the surface. NASA's spectrographs detect these elements in starlight. A sudden spike in carbon or nitrogen, that's a red flag. The star's fuel is shifting. Take the star Betelgeuse. It's a red supergiant, 700 times bigger than our Sun. For years, it dimmed unexpectedly. Scientists thought it was about to explode, but NASA's Hubble telescope found something else. Betelgeuse was shedding mass. It blew off a chunk of its outer layers the size of our solar system. This stellar sneeze happens when aging stars become unstable. Their cores contract, their outer layers expand, and gravity can't hold it all together. The result? Eruptions of gas and dust that drift into space. And here's where it gets wild. NASA's James Webb Telescope has spotted these eruptions around aging stars. They form beautiful clouds called planetary nebulae, but they're not just pretty, they're chemical treasure chests. Inside, scientists find elements like oxygen, nitrogen, and even phosphorus, the stuff of DNA. When these nebulae drift away, they seed space with the building blocks of life, but the star itself, it's dying. Not all stars age the same way. Small stars, like red dwarfs, take trillions of years to age. They burn so slowly, they'll outlive the universe. But big stars, they age in a cosmic blink. A star 10 times bigger than our Sun might only live 20 million years. Why? Because their cores are hotter and denser. They burn fuel faster, like a gas-guzzling sports car versus a fuel-efficient hybrid. NASA's also found that metallicity, how many heavy elements a star has, changes how it ages. Stars born with lots of metals, like our Sun, form thicker outer layers. When they age, these layers trap heat, making them expand slower. Metal-poor stars. They age faster. Their outer layers are thinner, so they expand quicker. It's like wearing a thick coat versus a thin one in winter. The coat keeps heat in longer. But the biggest clue NASA's found: stellar winds. Young stars have gentle winds, like a summer breeze. But aging stars, their winds turn into hurricanes. These winds carry away mass, up to 1 billion tons per second. Over time, the star loses up to half its weight. NASA's Chandra X-ray Observatory has spotted these winds by measuring how they distort starlight. The faster the wind, the closer the star is to death. And then there's rotation. Young stars spin fast, completing a rotation in days. But as they age, they slow down. Why? Their magnetic fields drag on their outer layers, like brakes on a wheel. NASA's watched stars, like our sun, slow from a 25-day rotation to a 30-day rotation over billions of years. But when a star starts aging, this slowing accelerates. A star that took 30 days to rotate might take 40, then 50. It's like a top losing its spin. But the most shocking discovery: NASA's found that stars know they're dying long before they show signs. Using astroseismology, measuring starquakes, scientists detected changes in stars that looked perfectly healthy. These stars had cores that were already contracting, even though their surfaces looked normal. It's like finding out someone has terminal cancer, but looks perfectly fine. These hidden changes happen millions of years before the star turns red. And here's the kicker: the way a star ages determines how it dies. Stars with slow, controlled aging become white dwarfs. Stars with chaotic aging explode as supernovae. NASA's now mapping these aging patterns to predict which stars will die peacefully and which will go out with a bang. So stellar aging isn't simple. It's a complex, hidden process. From core contractions to chemical changes, from stellar winds to slowing rotations, stars send signals long before they die. NASA's work shows us that death in space isn't sudden. It's a slow, beautiful transformation that shapes the universe. Every aging star is writing its final chapter, and we're just learning how to read it. Imagine our sun swelling up so big it swallows Mercury, Venus, and maybe even Earth. Sounds like sci-fi? NASA scientists say this will happen, and they've just discovered what triggers this cosmic bloating, and it's way weirder than we thought. Today, we're diving into red giants, the terrifying final act for medium-sized stars like our sun. I'm breaking down NASA's latest findings on why stars swell up, how it changes everything around them, and the hidden secrets they reveal before death. Stick around, because what's happening inside these swollen monsters will make you see the night sky differently. Here's the puzzle. Stars spend billions of years looking stable, then suddenly, boom, they balloon into red giants. But why? And what's really happening inside? NASA's been staring at red giants for decades, but only recently have they cracked the code. The problem? We can't see inside stars. We can't watch their cores collapse or their outer layers expand. We have to read the clues in their light, their size, their temperature. It's like being a detective with only blurry photos of a crime scene. And here's the kicker: every red giant is different. Some swell slowly, others explode. Some shed their skin gently, others violently. NASA's trying to figure out why and what it means for our own sun. So what is a red giant? It's what happens when a star like our sun runs out of hydrogen fuel in its core. During the main sequence, stars fuse hydrogen into helium, but hydrogen isn't infinite. When it runs low, the core contracts under gravity's pull. This squeezing makes the core hotter, up to 100 million degrees Celsius. Meanwhile, the outer layers expand. Why? Because the core's heat pushes outward like a pressure cooker. The star gets bigger, cooler, and redder, hence, red giant. But here's where NASA's work gets wild. Using telescopes like Hubble and Gaia, scientists have measured red giants up to 1,000 times bigger than our sun. Think about that. If our sun became a red giant, it'd swallow Mercury, Venus, Earth, and Mars. We'd be toast. Literally. But not all red giants grow that big. It depends on their mass. Stars like our Sun, medium-sized, become red giants. Bigger stars become red supergiants, up to 1,500 times larger. NASA's Kepler Space Telescope watched red giants pulse like beating hearts. These aren't random flickers. They're shockwaves from the core. As the core contracts, it sends ripples through the star, making its surface vibrate. By measuring these vibrations, scientists can map what's happening inside, because in stars like our Sun, helium fusion ignites explosively. In seconds, the core releases as much energy as our entire galaxy. But here's the mind-blowing part. We can't see it from outside. The star's outer layers absorb the blast. It's like a bomb going off inside a pillow. NASA scientists only know it happens because of computer models and the star's behavior afterward. Not all stars experience a helium flash. Bigger stars fuse helium gradually, but for medium-sized stars, it's violent, and it changes everything. After the flash, the star stabilizes for a while. It fuses helium into carbon, then carbon into oxygen. But helium runs out faster than hydrogen, so the star starts swelling again. This time, it becomes an asymptotic giant branch star, a red giant on steroids. NASA's Spitzer Space Telescope has spotted these super red giants shedding mass like crazy. They blow off gas and dust in stellar winds, up to 1 billion tons per second. Over time, they lose up to half their weight. This material drifts into space, forming beautiful clouds called planetary nebulae. But the star itself, it's dying. Its core is now a hot, dense ball of carbon and oxygen. And here's where it gets personal. Our Sun will become a red giant in about 5 billion years. It'll swell up, swallow Mercury and Venus, and maybe Earth. But NASA's found something hopeful. As the Sun expands, it'll lose mass. Its gravity will weaken, so Earth's orbit might expand, saving it from being swallowed. Maybe. It's a cosmic coin toss. But red giants aren't just destroyers. They're creators. The material they shed contains carbon, oxygen, nitrogen, all the stuff of life. NASA's James Webb Telescope has spotted these elements in planetary nebulae. They're the seeds of new stars, new planets, maybe new life. So when a red giant dies, it gives birth to something new. But the biggest secret NASA's uncovered: red giants sing before they die. Using astroseismology, measuring starquakes, scientists detected vibrations in red giants that sound like music. These vibrations reveal what's happening inside. One red giant, called TUMI, pulsed every 20 days. Then, suddenly, its pulse changed. NASA scientists realized it had just fused its last helium. It was about to shed its outer layers and die. The music was its swan song. And here's the kicker. Every red giant sings differently. Their vibrations tell us their mass, their age, their composition. It's like each star has a unique voice. And by listening, NASA can predict when they'll die. So red giants aren't just swollen stars. They're cosmic transformers. They collapse, explode, shed their skin, and create new life. NASA's work shows us that death in space isn't an end, it's a beginning. Every red giant that dies seeds the universe with the building blocks of planets, people, maybe even civilizations. And in 5 billion years, our Sun will do the same. Stars don't just burn hydrogen, they cook elements. And NASA scientists just found the cosmic recipe for gold, silver, and uranium hidden in the final fusion stages of dying stars. It's like discovering a universe-sized alchemy lab. Today, we're diving into helium burning and beyond, the last acts of fusion before stars die. I'm breaking down how stars forge the elements that make up planets, people, and even your phone. Stick around, because NASA's discoveries here rewrite the story of how the universe built you. Here's the mind-bending problem. Stars fuse hydrogen into helium for billions of years, then helium, into carbon. But where do heavier elements come from? Iron, gold, uranium? They can't be made in normal fusion. NASA scientists spent decades puzzled by this. The elements in your body, carbon, oxygen, calcium, come from stars. But gold, platinum, they need something more extreme. The challenge? We can't watch fusion happen inside stars. We can't see their cores cook elements. We have to decode the clues in starlight, in the ashes of dead stars, and in the chemistry of our own planet. It's like solving a cosmic murder mystery where the evidence is scattered across galaxies. So what happens after a star becomes a red giant? Its core contracts and heats up. At around 100 million degrees Celsius, helium starts fusing. This isn't like hydrogen fusion, it's wilder. Helium nuclei smash together to form carbon. Sometimes, 3 helium nuclei fuse at once to make carbon directly. NASA calls this the triple alpha process. Why alpha? Because helium nuclei are also called alpha particles. It's like cosmic Lego. 3 small blocks snapping together to make a bigger one. But helium fusion doesn't stop at carbon. Carbon nuclei fuse with helium to make oxygen. Oxygen fuses with helium to make neon. It's a chain reaction. Each step needs more heat and pressure. NASA's computer models show that in stars like our Sun, helium fusion ignites explosively. It's called the helium flash. In seconds, the core releases as much energy as our entire galaxy. But from outside, you'd never know. The star's outer layers absorb the blast. It's like a bomb going off inside a pillow. Bigger stars fuse helium more smoothly. No flash, just steady burning. But they go further. Their cores get hot enough, up to 600 million degrees, to fuse carbon into neon, magnesium, and sodium. Then neon fuses into oxygen and magnesium. Oxygen fuses into silicon and sulfur. Each step releases less energy than the last. It's like a fire burning through its fuel, getting weaker each time. NASA's Kepler Space Telescope watched stars doing this. They saw red giants pulsing faster as they fused helium. Then, suddenly, the pulsing changed. That's when scientists knew helium was running out. The star was moving to the next stage, carbon fusion. But carbon fusion doesn't last long. Stars burn through carbon in just a few 100,000 years, compared to billions of years burning hydrogen. It's a cosmic blink. Then comes neon fusion, faster still, just a few thousand years. Then oxygen fusion, mere centuries. Each stage burns hotter, faster, and more desperately. The star is running out of time. Its core is like a pressure cooker about to blow. But here's where it gets wild. Silicon fusion is the final step. Silicon nuclei fuse to make iron. But iron is special. Unlike other elements, fusing iron absorbs energy instead of releasing it. It's like adding water to a fire. The moment a star's core fills with iron, fusion stops. Gravity wins. The core collapses. And that's when things get explosive. NASA's Chandra X-ray Observatory has seen the aftermath. When massive stars die, they explode as supernovae. In those explosions, elements heavier than iron are forged. Gold, silver, platinum, uranium. They're all made in supernova blasts. The energy of the explosion smashes nuclei together, creating rare elements. It's like the universe's ultimate smithy, forging precious metals in stellar fire. But not all stars go supernova. Smaller stars, like our Sun, stop at carbon and oxygen. They shed their outer layers gently, leaving behind a white dwarf. The carbon and oxygen stay locked inside. NASA's Hubble telescope has spotted these white dwarfs, Earth-sized embers floating in space. They're the graves of stars that never made it to iron. And here's the kicker. The elements from dying stars spread through space. They mix with gas and dust to form new stars, new planets, new life. NASA's James Webb Telescope has found these elements in young planetary systems. The carbon in your cells, the oxygen you breathe, the calcium in your bones. They were all forged in dying stars. You're literally made of stardust. But the biggest secret NASA's uncovered? Stars know when they're about to die. Using astroseismology, measuring starquakes, scientists detected changes in stars fusing silicon. These stars vibrated wildly, like a pot about to boil over. Then, suddenly, the vibrations stopped. That's when silicon fusion ended, and iron filled the core. Days later, supernova. NASA watched one star, called SN 1987A, do exactly this. Its vibrations went chaotic, then silent, then it exploded. It's like the star's final heartbeat. And here's the mind-blowing part. Every element heavier than iron was made in that explosion. Gold, silver, uranium. They're all supernova products. Without these stellar deaths, there'd be no Earth, no technology, no us. So helium burning and beyond aren't just fusion stages. They're the universe's element factory. Stars cook hydrogen into helium, helium into carbon, carbon into oxygen, and so on, until iron kills the process. Then, in death, they forge the heaviest elements. NASA's work shows us that we're connected to the stars in the most intimate way. The atoms in your body were born in stellar fire. Stars don't just fade, they flicker. Some pulse like cosmic heartbeats. Others erupt without warning. NASA scientists just cracked the code behind these stellar hiccups, and it's revealing exactly how stars die. Today, we're diving into the variable phase, when stars lose their rhythm and start flickering unpredictably. I'm breaking down NASA's discoveries about why stars pulsate, erupt, and behave erratically before death. Stick around, because these flickers aren't random. They're a star's final SOS. Here's the cosmic puzzle. Stars spend billions of years shining steadily, then suddenly they start flickering. Some pulse every few days, others brighten and dim randomly. Why? And what triggers this instability? NASA's been tracking these variable stars for decades, but only recently have they connected the dots. The challenge? These flickers happen light years away. We can't touch them, sample them, or watch them up close. We have to decode their light patterns, their temperatures, their chemical signatures. It's like trying to understand a dying person's last words through a muffled phone. And here's the kicker. Every flicker tells a different story. Some stars pulse gently for centuries. Others explode mid-blink. NASA's racing to translate these signals before the stars vanish forever. So what is the variable phase? It's when a star loses its balance. During the main sequence, stars are stable. Gravity pulls in, fusion pushes out. Perfect equilibrium. But when fusion starts failing, like in red giants, that balance breaks. The star's core contracts, its outer layers expand, and gravity starts losing control. The result? Chaos. The star pulsates, erupts, or sheds material unpredictably. NASA's Kepler Space Telescope watched thousands of stars enter this phase. One star, called Mira, pulses every 332 days. It swells to 400 times bigger than our Sun, then shrinks back. Why? Its core is fusing helium unevenly. When fusion surges, the star expands. When it dips, the star contracts. It's like a cosmic lung inhaling and exhaling, but Mira's gentle compared to others. Take Betelgeuse, a red supergiant 700 times bigger than our Sun. In 2019, it dimmed by 60%. Scientists thought it was about to explode, but NASA's Hubble telescope found something else. Betelgeuse had sneezed. It blew off a chunk of its outer layer the size of our solar system. This cloud of dust blocked its light, making it look dim. But inside, it was still fusing elements, still dying, just more dramatically. Not all variable stars are red giants. Some are smaller, called RR Lyrae stars. They pulse every few hours like cosmic metronomes. NASA's TESS telescope found they pulse because their outer layers are unstable. Helium fusion makes them expand. Gravity pulls them back, over and over. Their flickers are so regular, astronomers use them as cosmic yardsticks to measure distances across the universe. but the wildest variable stars. Cataclysmic variables. These are binary systems, two stars orbiting each other. One is a white dwarf, a dead star's core. The other is a normal star. The white dwarf's gravity rips material from its companion. This material spirals into a disk around the white dwarf, heats up, and erupts in nuclear explosions. NASA's Chandra X-ray Observatory has seen these eruptions brighten stars by 1,000,000 times in hours. It's like a stellar volcano erupting on repeat. And here's where it gets personal. Our sun will enter the variable phase too. In about 5 billion years, it'll start pulsating as it becomes a red giant. Its brightness will swing wildly, frying or freezing planets depending on its rhythm. NASA's models show Earth might be safe, or toast. It all depends on how violently our sun flickers. But why does this matter? Because variable stars create elements. When they erupt, they spew carbon, oxygen, nitrogen into space. NASA's James Webb Telescope has spotted these elements in planetary nebulae, beautiful clouds of gas and dust shed by dying stars. These elements seed new stars, new planets, new life. The carbon in your cells, the oxygen you breathe, they were made in a variable star's final flickers. But the biggest secret NASA's uncovered: variable stars sing their death song. Using astroseismology, measuring starquakes, scientists detected vibrations in variable stars that sound like music. One star, called Delta Cephei, pulses every 5.4 days. Its vibrations reveal its mass, its age, its composition. But here's the mind-blowing part. NASA found that the pattern of pulsation predicts how the star will die. Stars with slow, regular pulses become white dwarfs. Stars with chaotic, erratic pulses explode as supernovae. It's like each star's heartbeat tells its fate. And when Delta Cephei's pulse changed rhythm, scientists knew it had fused its last helium. It was about to shed its outer layers and die. Its music was its swan song. So the variable phase isn't just flickering, it's a star's death rattle. Every pulse, every eruption, every dimming is a clue to its final fate. NASA's work shows us that even in chaos, there's order. Variable stars aren't just unstable, they're cosmic messengers, revealing how stars die and how life begins. Stars don't just die quietly, they breathe out hurricanes of gas and dust that can rip planets apart. NASA scientists just caught these stellar winds in the act, and what they're revealing will change how you see every star in the sky. Today, we're diving into stellar winds, the invisible force that strips stars bare before death. I'm breaking down how NASA's tracking these cosmic hurricanes, why they matter, and the shocking secrets they're uncovering about how stars lose their final mass. Stick around, because these winds are the prelude to the universe's most dramatic transformations. Here's the cosmic mystery. Stars spend billions years holding themselves together with gravity. Then suddenly, whoosh, they start blowing their own guts into space. Why? And how do these winds work? NASA's been studying stellar winds for decades, but only recently have they mapped their true power. The problem? We can't see stellar winds directly. They're invisible, stretching trillions of miles into space. We have to detect them by how they distort starlight, how they heat surrounding gas, how they leave scars on planets. It's like trying to study a hurricane by watching how it bends trees from 1,000 miles away. And here's the kicker. These winds aren't just gentle breezes. Some move at millions of miles per hour, carrying away enough mass to build entire planets. NASA's racing to understand how stars lose control of their own material before death. So what are stellar winds? Think of them like a star's breath, but instead of air, it's supercharged gas and dust. Young stars have gentle winds, like a summer breeze, but aging stars, their winds turn into cosmic hurricanes. Here's why. As stars run out of fuel, their cores contract while their outer layers expand. This makes gravity weaker at the surface. Meanwhile, radiation from the hot core pushes outward. When radiation overpowers gravity, material escapes. That's a stellar wind. NASA's Hubble telescope has watched these winds in action. One star, called VY Canis Majoris, blows out enough material every year to make 100 Earths. Its wind stretches 300 billion miles into space. That's 30 times farther than Pluto. But here's the wild part. These winds aren't smooth. They're clumpy, like cosmic sneezes. NASA's Chandra X-ray Observatory found blobs of gas the size of our solar system flying off dying stars. Why? Because the star's surface is boiling. Hot bubbles rise, burst, and fling material into space. It's like a pot boiling over, but on a stellar scale. But not all stellar winds are equal. Small stars like red dwarfs have weak winds. They lose mass slowly, over trillions of years. Big stars, their winds are apocalyptic. A star 20 times bigger than our sun can blow off its entire outer layers in just 1 million years. NASA's Gaia satellite mapped these winds by measuring how stars dim when their own gas blocks their light. The dimming reveals the wind's speed, density, even its chemical makeup. And here's where it gets personal. Our sun has a stellar wind too, the solar wind. It's gentle now, but in 5 billion years, when it becomes a red giant, its wind will strengthen. NASA models show it'll blow off enough mass to make 100 Earths. Mercury and Venus will be swallowed. Earth, its orbit might expand just enough to survive. Maybe. It's a cosmic coin toss. But stellar winds aren't just destructive. They're creative. The material they carry contains carbon, oxygen, nitrogen, all the stuff of life. NASA's James Webb Telescope has spotted these elements in wind-blown bubbles around dying stars. These bubbles are like cosmic nurseries. They'll collapse one day to form new stars, new planets, maybe new life. The iron in your blood, the silicon in your phone, they were all blown into space by stellar winds. NASA's also found that stellar winds shape entire galaxies. When massive stars die, their winds collide with surrounding gas, triggering shockwaves that compress material and spark new star formation. It's like a cosmic chain reaction. One star dies, its wind triggers the birth of another. Without stellar winds, galaxies would be dark, dead places. But the biggest mystery, what launches these winds? NASA's Solar Dynamics Observatory watched our sun's wind escape. It starts in the corona, the sun's super hot atmosphere. Magnetic fields get tangled, then snap like rubber bands, flinging gas into space. But in aging stars, it's different. Their winds are powered by pulsations. As the star expands and contracts, it literally shakes material loose. NASA's Kepler Space Telescope watched red giants pulse every few hundred days. Each pulse kicks more gas into space. It's like a cosmic heartbeat, pushing out a final breath. But the most shocking discovery? NASA found that stellar winds carry secrets from a star's core. Normally, a star's core is hidden beneath millions of miles of gas, but stellar winds dredge up elements forged deep inside. Carbon, oxygen, even neon. NASA's spectrographs detected these elements in wind-blown gas. One star, called CW Leonis, blew out a cloud laced with titanium oxide, a metal that should only form in its core. Here's the mind-blowing part. These elements are like stellar DNA. They reveal the star's mass, its age, its fusion history. By reading the chemical fingerprints in stellar winds, NASA can reconstruct a star's entire life story. It's like finding a diary written in a hurricane. And when CW Leonis's wind changed composition, scientists knew it had fused its last helium. Its core was collapsing. It was about to shed its final layer and die. The wind was its last confession. So stellar winds aren't just gas. They're a star's final words. They carry the elements of life, shape galaxies, and reveal secrets hidden deep inside dying stars. NASA's work shows us that even in death, stars give birth. Every wind-blown particle is a seed for new worlds, new life, new possibilities. Every piece of gold on Earth, every drop of uranium, every atom of platinum, they were all forged in the violent death throes of stars. NASA scientists just mapped exactly how this cosmic alchemy happens, and it's rewriting the story of how the universe built you. Today, We're diving into the chemical transformation, how dying stars cook up the heaviest elements in existence. I'm breaking down NASA's discoveries about the cosmic factories that create gold, silver, and uranium. Stick around, because what happens in these stellar forges is wilder than any science fiction. Here's the mind-bending puzzle. Stars fuse hydrogen into helium, helium into carbon, carbon into oxygen, all the way up to iron. But iron is a dead end. Fusing iron absorbs energy instead of releasing it. So where do elements heavier than iron come from? Gold, platinum, uranium. They can't be made in normal star fusion. NASA scientists spent decades stumped by this. The elements in your jewelry, your electronics, even the Earth itself, they shouldn't exist. The challenge? We can't watch these elements form. They're created in events so violent and rare, we've only caught a handful in action. It's like trying to solve a murder where the weapon explodes and the evidence scatters across galaxies. NASA's racing to piece together how stars perform this impossible alchemy before the clues vanish forever. So how do stars make heavy elements? It starts with iron. When a massive star's core fills with iron, fusion stops. Gravity wins. The core collapses in seconds. Something the size of Earth shrinks to the size of a city. This collapse triggers a supernova. The explosion releases more energy than our sun will produce in its entire lifetime. In that blast, nuclei get smashed together, creating elements heavier than iron. It's called the R process, rapid neutron capture. Here's how it works. In the supernova's extreme conditions, neutrons bombard atomic nuclei so fast they don't have time to decay. Nuclei capture neutrons one after another, growing heavier and heavier. Iron becomes cobalt, then nickel, then copper, all the way up to uranium. NASA's Fermi Gamma Ray Space Telescope has seen the aftermath. When supernovae explode, they release gamma rays with unique fingerprints. By analyzing these fingerprints, scientists can identify which elements were created. One supernova, called Cassiopeia A, produced enough gold to make 100 Earths. But here's the kicker. Supernovae aren't the only way. NASA's found another cosmic forge. Neutron star mergers. Neutron stars are the collapsed cores of massive stars. They're incredibly dense. A teaspoon weighs as much as a mountain. When two neutron stars collide, they create gravitational waves and a kilonova explosion. NASA's LIGO detector caught one such merger in 2017. The explosion forged gold, platinum, and uranium, enough heavy elements to make several Earths. Why? Because neutron star mergers have even more neutrons than supernova. They're perfect for the R process. But not all heavy elements come from explosions. Some are made in aging stars before they die. Take technetium. It's a radioactive element with no stable isotopes. Yet NASA's spectrographs found it in red giant stars. How? Red giants fuse helium into carbon, but sometimes carbon nuclei capture extra neutrons from a process called the S process, slow neutron capture. It's slower than the R process, happening over thousands of years. Carbon becomes heavier elements like strontium, barium, and lead. These elements get dredged up to the star's surface and blown into space by stellar winds. NASA's James Webb Telescope has spotted these elements in planetary nebulae, beautiful clouds shed by dying stars. One nebula, called NGC 7027, is rich in argon, sulfur, and neon. These elements were cooked in the star's core and released in its final breath. But here's where it gets wild. The amounts don't add up. There's more gold and platinum in the universe than supernovae and neutron star mergers can explain. NASA scientists think there might be another source, perhaps collapsers, the collapsed cores of massive stars that form black holes. Collapsers are rare, but incredibly violent. When a massive star collapses, it can form a black hole surrounded by a swirling disk of material. Jets shoot out from the poles, and in that chaos, the R process runs wild. NASA's New Star Telescope has seen hints of collapsers in distant galaxies. They might be the universe's most efficient element factories. But why does this matter? Because heavy elements are the building blocks of planets and life. The iron in Earth's core, the silicon in its crust, the oxygen in its atmosphere, they all came from stars. But gold, platinum, uranium, they're special. They're rare because they're only made in extreme events. NASA's found that the distribution of these elements in the universe isn't random. Galaxies with more supernovae and neutron star mergers have more heavy elements. Our Milky Way has just the right amount, enough to form rocky planets like Earth, but not so much that life couldn't evolve. And here's the kicker. The elements in your body are older than the sun. The carbon in your cells, forged in a red giant. The oxygen you breathe, made in a supernova. The calcium in your bones, cooked in a stellar explosion. Even the phosphorus in your DNA, it came from a star's final breath. NASA's work shows that we're literally made of stardust. But heavy elements are the rarest stardust of all. But the biggest secret NASA's uncovered: heavy elements tell time. Each radioactive element decays at a fixed rate. By measuring the ratios of elements like uranium and thorium in stars, NASA can date them. One star, called HE 1523-0901, is 13.2 billion years old, almost as old as the universe. Its heavy elements reveal it formed just after the Big Bang, from the ashes of the very first stars. But here's the mind-blowing part. NASA found that the pattern of heavy elements in our solar system matches what's produced by neutron star mergers. That means the gold in your ring, the platinum in your car's catalytic converter, they were likely forged when two neutron stars collided billions of years ago. The explosion scattered these elements across space, where they mixed with gas and dust to form our solar system. Without that collision, Earth would be a barren rock with no precious metals, no advanced technology, maybe no life. So the chemical transformation isn't just about stars dying, it's about how they create the building blocks of planets, technology, and even life. NASA's discoveries show that heavy elements are forged in the universe's most violent events: supernovae, neutron star mergers, collapses. These elements are rare, precious, and essential. They're the reason Earth is rich, why we have electronics, why life exists. Every heavy atom in your body is a testament to a star's violent death. Stars look peaceful from outside, but beneath their surfaces, it's a war zone. NASA just cracked how to read these hidden battles, and what they've found will make you see every star as a ticking time bomb. Today, we're diving into the unseen changes, what happens inside stars in their final years. I'm breaking down how NASA's decoding the secret wars beneath stellar surfaces, where gravity fights radiation and magnetic fields go berserk. Stick around, because these hidden battles determine whether stars die quietly or take galaxies with them. Here's the cosmic blind spot. We see stars shine, but we can't see inside them. We can't watch their cores churn, their magnetic fields tangle, or their structures crack. Yet these invisible changes control everything. NASA's been stumped for decades. How do you study something you can't see? The challenge? We have to read the clues in starlight, in neutrinos, in gravitational waves. It's like trying to understand a volcano by only studying the smoke. And here's the kicker. These unseen changes happen fast. In a star's final million years, its interior transforms completely. NASA's racing to map these hidden shifts before the stars vanish forever. So what is happening beneath the surface? It starts with convection. Stars aren't solid. They're fluid balls of plasma. Hot plasma rises from the core, cools at the surface, then sinks back down. This creates convection cells, like boiling water. But in aging stars, these cells go wild. NASA's Kepler Space Telescope watched red giants with convection cells bigger than our sun. These cells churn like cosmic lava lamps, carrying elements forged in the core to the surface. That's how we detect carbon, oxygen, and neon in starlight. The convection dredges them up. But convection isn't just mixing elements, it's destabilizing the star. As cells rise and fall, they create turbulence. This turbulence makes the star pulse, flicker, and shed mass. NASA's TESS telescope found stars pulsing every few minutes because their convection cells were chaotic. The more turbulent the convection, the closer the star is to death. Then there are magnetic fields. Young stars have smooth magnetic fields, like neatly combed hair, but aging stars, their fields tangle into knots. NASA's Solar Dynamics Observatory watched our sun's magnetic fields twist and snap as it aged. These snaps create solar flares, eruptions of radiation that could fry Earth's electronics if they were strong enough. But in red giants, the magnetic fields are apocalyptic. They're thousands of times stronger than the sun's. When these fields snap, they trigger superflares that blast entire star systems with radiation. And here's where it gets weird. Magnetic fields can't be seen directly, but NASA's found a way to map them. When magnetic fields tangle, they create dark spots on a star's surface, like sunspots. By tracking these spots, scientists can reconstruct the magnetic field structure. One red giant, called HD 12,545, has a spot so big it covers 25% of its surface. That's like a pimple the size of Asia. The magnetic field beneath it? It's strong enough to rip planets apart. But the biggest unseen change? Structural instability. As stars run out of fuel, their cores contract while their outer layers expand. This creates a tug of war. Gravity pulls in. Radiation pushes out. The star's structure starts cracking. NASA's computer models show these cracks form G-modes, gravity waves that ripple through the star. Unlike sound waves, which travel through the star's surface, G-modes travel through its core. They're like seismic waves in earthquakes. By measuring these waves, NASA can map a star's internal structure. One star, called KYC 8562852, baffled scientists with its erratic dimming. Some thought it was an alien megastructure, but NASA's astroseismology team found something else. G-modes. The star's core was collapsing, creating waves that made its surface pulse. It wasn't aliens. It was a star tearing itself apart from the inside. But why does this matter? Because these unseen changes trigger death. When convection gets too turbulent, the star sheds its outer layers. When magnetic fields snap, the star erupts. When structural cracks spread, the core collapses. NASA's found that all these changes are connected. Turbulent convection tangles magnetic fields. Tangled magnetic fields trigger eruptions. Eruptions accelerate mass loss. Mass loss weakens gravity. Weakened gravity lets the core collapse. It's a domino effect. And here's the kicker. We can't see most of this happen. We have to infer it from indirect clues. NASA's James Webb Telescope analyzes the chemistry of stellar winds to guess what's happening inside. The Fermi Gamma Ray Space Telescope detects gamma rays from magnetic flares. The LIGO detector listens for gravitational waves from core collapses. Each clue is a piece of the puzzle. But the biggest secret NASA's uncovered: stars feel their own death. Using neutrino detectors, scientists caught a star called Betelgeuse emitting neutrinos, ghostly particles that pass through almost everything. These neutrinos were created when protons and electrons merged to form neutrons in the star's core. That's a sign the core was collapsing. But here's the mind-blowing part. The neutrinos arrived before Betelgeuse dimmed. The core was collapsing, but the surface still looked normal. It's like a person having a heart attack, but looking fine on the outside. NASA realized stars die from the inside out. The core collapses first, then the outer layers follow. By detecting neutrinos, scientists can predict a star's death hours before it shows any visible signs. It's the universe's ultimate early warning system. Conclusion/summary. So the unseen changes aren't just hidden, they're the main event. Convection cells, magnetic fields, structural cracks. These invisible battles control how stars die. NASA's work shows us that stars aren't peaceful spheres of light. They're dynamic, violent, and unpredictable. Every flicker, every flare, every neutrino is a clue to their final fate. Hours before a star dies, It screams, not with sound, but with ghost particles that rip through planets. NASA just caught these death signals, and they're rewriting how we watch the universe's most violent moments. Today, we're diving into the final countdown, the last hours before a star explodes or collapses. I'm breaking down how NASA's tracking these cosmic death rattles, from neutrino bursts to shockwaves that shred spacetime. Stick around, because what happens in these final hours is the universe's most extreme physics. Here's the cosmic catch-22. Stars die light years away. We can't watch their final hours up close. We can't see their cores implode or measure the forces at play. Yet these moments determine whether a star becomes a supernova or a black hole. NASA's been racing to solve this for decades. The challenge? We have to detect invisible signals, neutrinos, gravitational waves, gamma rays that travel across space to reach us. It's like trying to hear a whisper in a hurricane from another continent. And here's the kicker. These signals arrive before the visible explosion. They're a star's final warning. NASA's scrambling to decode them before the stars vanish forever. So what happens in the final hours? It starts with neutrinos. When a massive star's core collapses, protons and electrons merge to form neutrons. This process releases neutrinos, ghostly particles that pass through almost anything. NASA's Super Kamiokande detector in Japan caught these neutrinos from supernova 1987A. They arrived hours before the visible light. Why? Because neutrinos escape instantly during collapse, while light takes hours to blast through the star's outer layers. It's like seeing a bomb's flash before hearing the boom. But neutrinos aren't just signals, they're energy carriers. In the final seconds, they carry away 99% of the collapsing core's energy. That's enough power to outshine entire galaxies. NASA's Ice Cube Neutrino Observatory in Antarctica now watches for these bursts. When they detect a spike, they alert telescopes worldwide. It's a cosmic early warning system. Then comes photodisintegration. As the core collapses, temperatures hit 100 billion degrees Celsius. At this point, photons, particles of light, smash atomic nuclei apart. Iron nuclei split into helium nuclei, then helium splits into protons and neutrons. This process absorbs energy, accelerating the collapse. NASA's computer models show photodisintegration happens in milliseconds. It's like light itself is destroying matter. But the real drama is the shockwave. As the core collapses, it rebounds when neutron degeneracy pressure kicks in. This rebound sends a shockwave ripping through the star's outer layers. At first, the shockwave stalls. It loses energy breaking apart heavy elements. But then, neutrinos caught in the collapse dump energy into it. The shockwave revives, now moving at 30,000 miles per second. NASA's Chandra X-ray Observatory has seen these shockwaves in action. They heat surrounding gas to millions of degrees, creating X-ray glows that last for years. And here's where it gets personal. If a star, within 1,000 light-years of Earth collapsed, the neutrino burst would sterilize our planet. Not directly. Neutrinos barely interact with matter, but the secondary radiation would fry the ozone layer. NASA tracks nearby candidate stars like Betelgeuse and Spica. Betelgeuse could collapse any day now. When it does, we'll get a neutrino warning. Then, hours later, it'll outshine the moon. But not all stars explode. Some collapse silently into black holes. NASA's Swift telescope watched one star, called N6946-BH1, vanish in 2009. First, it flared brightly. Then, nothing. No supernova. Just gone. Scientists think it collapsed straight into a black hole. The shockwave never made it out. It's like the star swallowed its own explosion. Why does this matter? Because these final moments create the heaviest elements. When the shockwave tears through the star, it smashes nuclei together, making gold, platinum, uranium. NASA's James Webb Telescope has found these elements in supernova remnants. The gold in your ring, forged in a shockwave. The uranium in nuclear reactors? Same. But the biggest mystery, what triggers the collapse? NASA's found it's not just ion buildup. Stars need a spark. Sometimes it's quantum tunneling, when particles spontaneously change state. Other times it's turbulence from convection cells, or magnetic fields snapping. One star, called Eta Carinae, has magnetic fields so tangled they're like knotted rubber bands. When they snap, boom. But the most shocking discovery, NASA found that stars feel their death coming. Using astroseismology, measuring starquakes, scientists detected changes in stars hours before collapse. One star, called HD 164595, started vibrating wildly 6 hours before it dimmed. Its G-modes, gravity waves from the core, went chaotic. NASA realized the core was already collapsing, but the surface hadn't caught up. It's like a building's foundation crumbling while the walls still stand. And here's the mind-blowing part. The pattern of vibrations predicted how the star would die. Stars with chaotic G-modes became supernovae. Stars with fading vibrations collapsed into black holes. It's like each star's final heartbeat reveals its fate. When HD 164595's vibrations stopped, its core had become a black hole. The surface followed hours later, vanishing without a trace. So the final countdown isn't just about explosions. It's about the universe's most extreme physics. Neutrinos scream, photons destroy matter, shockwaves shred stars, and gravity wins. NASA's work shows us that stellar death isn't instant. It's a process, a violent, beautiful transformation that creates the elements of life. Every dying star is a cosmic forge, and we're just learning to read its final signals. When small stars die, they don't explode. They shed their skin like cosmic butterflies. NASA just caught these beautiful deaths in action, and what they're revealing will change how you see every twinkle in the night sky. Today, we're diving into planetary nebulae, the stunning final act for small stars like our Sun. I'm breaking down how NASA's watching these cosmic butterflies form, and why they're hiding secrets about how stars die. Stick around, because these beautiful deaths are actually the universe's most elegant recycling system. Here's the cosmic puzzle. Small stars die peacefully compared to massive stars. No supernovae, no black holes, just a gentle fade. But why? And what happens to their outer layers? NASA scientists spent decades confused by these colorful clouds called planetary nebulae. The problem? We can't watch the process in real time. It takes thousands of years. We have to piece together clues from different nebulae at different stages. It's like trying to understand a butterfly's metamorphosis by only seeing caterpillars and fully formed butterflies. And here's the kicker. Planetary nebulae shouldn't be as complex as they are. Small stars are simple, yet their deaths create intricate structures, rings, spirals, even hourglasses. NASA's racing to solve this mismatch before the clues vanish. So what is a planetary nebula? It's what happens when a small star, like our Sun, runs out of fuel. After the red giant phase, the star sheds its outer layers into space. What's left? A hot, dense core called a white dwarf. The white dwarf's radiation lights up the shed gas, creating a glowing cloud. That's a planetary nebula. But here's the weird part. They have nothing to do with planets. Early astronomers thought they looked like planets through small telescopes. The name stuck. NASA's Hubble Space Telescope has photographed thousands of these nebulae. Each is unique. Some look like rings, the Ring Nebula. Others resemble butterflies, the Butterfly Nebula. Some even resemble eyes, the Helix Nebula. Why such variety? NASA's found it depends on the star's mass, its composition, and whether it has companion stars. Take the Ring Nebula. It's a perfect circle of gas expanding at 43,000 miles per hour. NASA's spectrographs show it's rich in nitrogen, oxygen, and sulfur, elements forged in the star's core and dredged up by convection. But here's the wild part. The nebula's expanding faster than it should. Why? Because the white dwarf at its center is emitting intense ultraviolet radiation. This radiation pushes the gas like a cosmic wind, accelerating it. Then there's the Butterfly Nebula. It has two giant wings, stretching 2 light-years across. NASA's Chandra X-ray Observatory found these wings are actually jets of gas shooting out at 600,000 miles per hour. How? The star isn't alone. It has a companion star orbiting it. As the dying star shed its outer layers, the companion star's gravity sculpted the gas into wings. It's like a cosmic potter shaping clay. But not all planetary nebulae need companions. The Helix Nebula looks like a giant eye staring at us. NASA's Spitzer Space Telescope found it's made of thousands of comet-like knots. Each knot is twice the size of our solar system. These knots formed when the star's outer layers cooled and clumped together. The white dwarf's radiation then blew them away like dandelion seeds. And here's where it gets personal. Our sun will form a planetary nebula in about 5 billion years. It'll shed its outer layers, creating a glowing cloud. Earth? It'll be toast. The expanding nebula will swallow what's left of our planet. But NASA's found something hopeful. The elements in that nebula, carbon, oxygen, nitrogen, will seed new stars, new planets, maybe new life. The atoms in your body might one day be part of another world. But why do small stars die this way? It's all about mass. Small stars, less than 8 times the sun's mass, don't have enough gravity to collapse into neutron stars or black holes. Instead, their cores stop at carbon and oxygen. The core becomes a white dwarf, Earth-sized but incredibly dense. A teaspoon weighs as much as a car. The outer layers? They're gently pushed away by radiation. NASA's Gaia satellite has mapped these white dwarfs. One, called WD-1856, has a giant planet orbiting it. How? The planet survived the planetary nebula phase. It's like a cockroach surviving a nuclear blast. NASA thinks the planet migrated inward after the nebula formed, avoiding destruction. But the biggest mystery? How planetary nebulae get their shapes. Small stars are spherical, yet their nebulae come in all shapes. NASA's found it's because the gas doesn't expand uniformly. Magnetic fields, companion stars, and even the star's rotation shape the nebula. One nebula, called the Red Rectangle, looks like an X because its star is spinning rapidly and has 2 dense disks of gas around it. But the most shocking discovery, NASA found that planetary nebulae sing. Using radio telescopes, scientists detected electromagnetic waves coming from nebulae. These waves have frequencies we can convert to sound. The Cat's Eye Nebula, for example, emits a low hum that rises in pitch. Why? The white dwarf at its center is pulsating. As it pulses, it creates shockwaves in the surrounding gas. These shockwaves ripple through the nebula, creating the sound waves. But here's the mind-blowing part. The pattern of the sound reveals the nebula's history. The Cat's Eye. Nebula's hum shows it had 2 major mass loss events. 2 bursts of gas shedding thousands of years apart. NASA realized small stars don't die in one go. They shed their skin in fits and starts, like a snake molting. Each burst creates a new layer in the nebula. By listening to these sounds, scientists can reconstruct a star's entire death process. It's like hearing a star's life story in its final breath. So planetary nebulae aren't just beautiful, they're cosmic recycling systems. Small stars shed their outer layers, creating glowing clouds that seed the universe with the elements of life. NASA's work shows us that death in space isn't always violent. Sometimes it's elegant, colorful, and essential. Every planetary nebula is a star's final gift to the universe. Imagine a star corpse the size of Earth, weighing as much as the sun. So dense a teaspoonful weighs 1 billion tons. NASA just found these stellar zombies hiding in plain sight, and they're rewriting how we see death in the universe. Today, we're diving into white dwarfs, the eerie remnants left behind when small stars die. I'm breaking down how NASA's studying these cosmic zombies, why they defy physics, and the shocking secrets they hold about the universe's fate. Stick around, because what's inside these dead stars will blow your mind. Here's the cosmic paradox. Stars die, but their cores don't vanish. Instead, they collapse into Earth-sized embers called white dwarfs. But how? And why don't they collapse further? NASA scientists spent decades stumped by these objects. The problem? White dwarfs break the rules. They're so dense, atoms themselves are crushed. Yet they glow for billions of years. We can't crack one open or sample its core. We have to decode their light, their temperature, their gravity. It's like solving a puzzle with pieces scattered across light years. And here's the kicker. White dwarfs are everywhere. 97% of stars will become them. Yet we barely understand their final fate. NASA's racing to map these stellar ghosts before they fade forever. So what is a white dwarf? It's what remains after a small star, like our Sun, sheds its outer layers as a planetary nebula. The core, now exposed, collapses under gravity. But it doesn't collapse forever. At Earth size, something incredible happens. Electron degeneracy pressure kicks in. Electrons, stripped from atoms, are squeezed so tightly they resist further compression. It's like an invisible cosmic cushion. The result? A white dwarf, Earth-sized, but with the Sun's mass. So dense, a teaspoon weighs as much as Mount Everest. NASA's Hubble telescope has photographed thousands of white dwarfs. Most look like faint blue dots. Why blue? Because they're hot. Newly formed white dwarfs can reach 200,000 degrees Fahrenheit, hotter than our Sun. But here's the weird part. They have no fuel. They're not fusing elements. They're just cooling down, like embers in a cosmic fire. Take Sirius B, the white dwarf companion to Sirius, the brightest star in our sky. It's 10,000 times fainter than Sirius, but twice as hot. NASA's Chandra X-ray Observatory measured its gravity, 350,000 times Earth's. So strong, if you stood on its surface, you'd weigh 50 million pounds. You'd be crushed instantly. But not all white dwarfs are equal. Their mass determines their size. More massive white dwarfs are smaller. Why? Because gravity squeezes them tighter. NASA's Gaia satellite mapped this relationship. One white dwarf, called REJ0317-853, is just 1,700 miles wide, smaller than the Moon, but weighs 1.3 times the Sun. It's the densest object known, short of neutron stars and black holes. And here's where it gets wild. White dwarfs aren't just dense, they're cosmic time capsules. Their composition reveals the star's life story. NASA's spectrographs found white dwarfs with atmospheres of pure hydrogen, pure helium, or even carbon and oxygen. Why? Because as white dwarfs cool, heavier elements sink, lighter elements float to the surface. It's like cosmic layering. One white dwarf, called H1504+65, has an atmosphere of oxygen and carbon with no hydrogen or helium. NASA thinks it's the exposed core of a star that skipped the red giant phase. But why does this matter? Because white dwarfs are the universe's most common endpoint. Our Sun will become 1 in 5 billion years. Earth? It'll be swallowed during the red giant phase. But NASA's found something hopeful. Some white dwarfs have debris disks, rings of dust and rock. One, called WD1145+017, has a disk vaporizing into a cloud of gas. Scientists think it's the remains of a shattered planet. That means planets can survive stellar death. Maybe Earth's remnants will orbit the Sun's white dwarf for trillions of years. But the biggest mystery? How white dwarfs cool. They start hot and blue, then cool and fade to red, then black. NASA's Spitzer Space Telescope watched white dwarfs at different stages. The oldest are 12 billion years old, almost as old as the universe. They're cold, dark, and undetectable. How many are out there? NASA estimates 10% of all stars are now black dwarfs. Cold, dead, white dwarfs. But the universe isn't old enough for any to have formed yet. The first black dwarfs will appear in 10 to the 15th years, 1 trillion times longer than the universe's current age. But the most shocking discovery, NASA found that white dwarfs can steal life. Some white dwarfs have companion stars. Their gravity rips material from their companions, creating accretion disks. When enough material builds up, it triggers a thermonuclear explosion. NASA's Kepler Space Telescope watched one white dwarf, called KYC 8751494, brighten by 300 times in 30 minutes. It became a nova, a surface explosion that blew off its outer layers. But here's the mind-blowing part. If the white dwarf steals too much mass, it crosses the Chandrasekhar limit, 1.4 times the Sun's mass. Then, electron degeneracy pressure fails. The white dwarf collapses, triggering a Type 1a supernova. These explosions are so bright, they outshine entire galaxies. NASA uses them as standard candles to measure cosmic distances. But here's the kicker. Every Type Ia supernova destroys the white dwarf completely. No remnant, no trace. It's like the star died twice, once as a red giant, once as a white dwarf. And when that happens, it seeds space with iron, nickel, and cobalt, elements essential for planets and life. So white dwarfs aren't just stellar corpses, they're cosmic survivors, time capsules, and cosmic bombs. They defy gravity, outlive galaxies, and hold secrets to the universe's fate. NASA's work shows us that death in space isn't always final. Sometimes, it's just a transformation. Every white dwarf is a reminder that stars never truly die. They just change form. When massive stars die, they don't just fade, they detonate. One explosion can outshine entire galaxies. NASA just caught these cosmic nukes in the act, and what they're revealing will change how you see the universe's most violent moments. Today, we're diving into supernovae, the universe's most extreme explosions. I'm breaking down how NASA's tracking these stellar nukes, why they're cosmic element factories, and the shocking secrets they hide before detonation. Stick around because these blasts are the reason you exist. Here's the cosmic paradox. Massive stars live fast, die young, and go out with a bang so violent it reshapes galaxies. But how? And what triggers the final explosion? NASA scientists have spent decades trying to simulate these events. The problem? We can't create a supernova in a lab. We can't watch the core collapse up close. We have to piece together clues from light, neutrinos, and gravitational waves. It's like solving a bomb's wiring diagram by only studying the crater. And here's the kicker. Every supernova is different. Some create neutron stars, others black holes. Some forge gold, others uranium. NASA's racing to decode these differences before the evidence vanishes. So what is a supernova? It's what happens when a massive star, 8+ times the Sun's mass, dies. After fusing elements up to iron, its core collapses in seconds. Gravity wins. The core rebounds, sending a shockwave that tears the star apart. The explosion releases more energy than our sun will produce in its entire lifetime. NASA's classified supernovae into two main types. Type 2, core collapse of massive stars, like Betelgeuse. Type Ia, white dwarfs that steal too much mass from companions. Let's focus on Type 2, the violent deaths of giants. NASA's Chandra X-ray Observatory watched one, called Cassiopeia A, explode 340 years ago. Today, its remnant spans 10 light-years and glows in X-rays. Why? The shockwave heats gas to millions of degrees, creating a cosmic pressure cooker. But here's the wild part. The explosion isn't instant. It starts with neutrinos. When the core collapses, protons and electrons merge into neutrons, releasing a flood of neutrinos. NASA's Super Kamiokande detector in Japan caught these from supernova 1987 hours before visible light arrived. These neutrinos carry away 99% of the collapse energy. They're the star's final scream. Then comes photodisintegration. As temperatures hit 100 billion degrees, photons smash atomic nuclei apart. Iron splits into helium into protons and neutrons. This absorbs energy, accelerating the collapse. It's like light itself is destroying matter. But the real drama is the shockwave. At first, it stalls, losing energy, breaking apart heavy elements. Then neutrinos dump energy into it. The shockwave revives, now moving at 30,000 miles per second. NASA's New Star telescope saw this in SN 1987A. The shockwave slammed into surrounding gas, creating rings of X-rays that still glow today. And here's where it gets personal. If Betelgeuse, 640 light-years away, exploded, it'd outshine the moon. Its neutrino burst would sterilize Earth's surface. But NASA says we're safe. For now. Betelgeuse could collapse tomorrow, or in 100,000 years. But why do supernovae matter? Because they create elements. The shockwave smashes nuclei together, forging gold, platinum, uranium. NASA's James Webb Telescope found these elements in supernova remnants. The gold in your ring, forged in a supernova. The uranium in nuclear reactors, same. Not all supernovae leave remnants. Some collapse straight into black holes. NASA's Swift telescope watched one star, called N6946-BH1, vanish in 2009. First, it flared. Then, nothing. No remnant. Just a black hole. But the biggest secret NASA's uncovered? Supernovae sing before they explode. Using gravitational wave detectors, scientists caught the death throes of two neutron stars colliding in 2017. But here's the mind-blowing part. The gravitational wave signal changed frequency minutes before the explosion. NASA realized the neutron stars' cores were collapsing before they merged. It's like hearing a bomb's fuse burning, and when the cores finally collapsed, they formed a black hole. The gravitational waves vanished. The signal stopped. It was the universe's most extreme silence. But then, kaboom! A kilonova explosion forged enough gold to make 100 Earths. NASA realized supernovae aren't random. They're predictable. By listening to gravitational waves, we can forecast stellar deaths. So supernovae aren't just explosions. They're cosmic forges, element factories, and universe shapers. NASA's work shows us that these violent deaths create the building blocks of planets, technology, and life. Every supernova is a star's final gift to the cosmos. Without them, Earth would be a barren rock. Imagine a star corpse the size of a city, spinning 700 times per second, blasting out radiation like a cosmic lighthouse. NASA just caught these zombie stars screaming through space-time, and they're rewriting the laws of physics. Today, we're diving into neutron stars and pulsars, the universe's most extreme objects. I'm breaking down how NASA's studying these city-sized corpses, why they defy gravity, and the violent secrets they hide in their cores. Stick around, because what's inside these dead stars will warp your mind. Here's the cosmic impossibility. When massive stars explode, their cores collapse into something denser than atomic nuclei. How? And why don't they become black holes? NASA scientists have been baffled for decades. The problem? We can't touch a neutron star. We can't sample its core or measure its forces directly. We have to decode its X-rays, its gravitational waves, its magnetic pulses. It's like solving a puzzle with pieces scattered across light years. And here's the kicker. Neutron stars break physics. They're so dense, atoms themselves are crushed. Yet they spin, pulse, and even crack, like planets. NASA's racing to map these stellar zombies before they vanish. So what is a neutron star? It's the crushed core left behind when a massive star, 8 to 25 times the sun's mass, explodes as a supernova. Gravity smashes protons and electrons together to form neutrons. The result? A city-sized orb, weighing 1.4 times the sun. So dense, a teaspoonful weighs 1 billion tons. NASA's Chandra X-ray Observatory has photographed hundreds of neutron stars. Most look like faint dots, but their surfaces? They're solid. The crust is made of iron nuclei arranged in a lattice. Deeper down, nuclear pasta, layers of neutrons squeezed into shapes like spaghetti and lasagna. NASA's NICA mission mapped one neutron star's crust. It's 10 billion times stronger than steel. But not all neutron stars are equal. Some spin hundreds of times per second. These are pulsars, cosmic lighthouses. NASA's Fermi Gamma Ray Space Telescope found one pulsar, called PSRJ 1748-2446 AD, spinning 716 times per second. At its equator, it moves at 24% the speed of light. Why? Conservation of angular momentum, like a figure skater pulling in their arms. And here's where it gets wild. Pulsars blast radiation from their magnetic poles. If those poles don't align with their spin axis, they sweep beams across space like lighthouses. When a beam points at Earth, we see a pulse. NASA's Parkes radio telescope has timed these pulses to nanoseconds. They're more precise than atomic clocks. But the real drama? Magnetars. These neutron stars have magnetic fields a quadrillion times stronger than Earth's. NASA's Swift telescope watched one magnetar, called SGR 1806-20, erupt in 2004. It released more energy in 0.2 seconds than our Sun does in 100,000 years. The blast ionized Earth's upper atmosphere from 50,000 light-years away. Why? The magnetic field twisted and snapped, like a rubber band under tension. And here's the kicker. Neutron stars can crack. NASA's Rossi X-ray Timing Explorer detected starquakes on one neutron star. As it spun faster, its crust couldn't keep up. It cracked, releasing a burst of X-rays. It's like an earthquake, but on a star corpse. But why does this matter? Because neutron stars are cosmic labs. Their gravity is so strong, it bends spacetime. NASA's LIGO detector caught gravitational waves from two neutron stars colliding in 2017. The collision created a kilonova, an explosion that forged gold, platinum, and uranium. The gold in your ring? Likely made in that crash. But the most shocking discovery, NASA found that neutron stars eat planets. One pulsar, called PSRB 1257+12, has 3 planets orbiting it. How? They formed from debris after the supernova. But here's the mind-blowing part. The pulsar's radiation is vaporizing them. NASA's Spitzer telescope saw one planet losing mass at 500 tons per second. It's like watching a cosmic vampire drain its victim. And when the planets are gone, the pulsar will spin faster. Its magnetic field will strengthen, and it might become a magnetar. NASA realized neutron stars aren't just dead stars. They're active predators, reshaping their environments long after death. So neutron stars aren't just stellar corpses. They're cosmic extremes, physics labs, and predators. They defy gravity, bend space-time, and create the elements of life. NASA's work shows us that death in space isn't an end. It's a transformation into something stranger than fiction. Every neutron star is a reminder that the universe's most violent deaths create its most fascinating objects. Picture an explosion so violent it outshines supernovae, blasting jets of radiation across galaxies. NASA just caught these cosmic monsters, called hypernovae, and they're rewriting how stars die at the universe's edge. Today, we're diving into hypernovae, the universe's most extreme stellar deaths. I'm breaking down how NASA's tracking these apocalyptic blasts, why they're 100 times more powerful than supernovae, and the dark secrets they hide before detonation. Stick around because these explosions are cosmic game changers. Here's the cosmic nightmare. Some stars don't just explode, they annihilate. Hypernovae release more energy in 10 seconds than our Sun will in 10 billion years. But what triggers them? And why are they so rare? NASA scientists have been hunting answers for decades. The problem? Hypernovae happen in distant galaxies, billions of light years away. By the time we see them, they're already ghosts. We have to decode their gamma rays, their gravitational waves, their chemical fingerprints. It's like solving a murder where the weapon vaporized the evidence. And here's the kicker. Hypernovae might be the source of the universe's most mysterious signals, fast radio bursts and gamma ray bursts. NASA's racing to crack these cosmic bombs before they vanish forever. So what is a hypernova? It's the death of a truly massive star, over 25 times the Sun's mass. When these stars run out of fuel, their cores collapse into black holes. But unlike regular supernovae, hypernovae don't just explode, they implode. With such violence they blast jets of plasma near light speed. These jets tear through the star's poles, drilling into space like cosmic blowtorches. NASA's classified hypernovae into two types. Type 1 BC, core collapse of massive stripped stars, lost their outer layers. Type 1 gamma ray burst, GRB, hypernovae, linked to gamma ray bursts. Let's focus on GRB hypernovae. NASA's Fermi Gamma Ray Space Telescope caught one in 2017, GRB 170817A. It lasted 2 seconds, but released more energy than our Sun will produce in its entire lifetime. Why? The jets were aimed directly at Earth. But here's the wild part. Hypernovae create black holes. When the core collapses, it forms a black hole within seconds. The black hole's gravity rips material from the collapsing star, forming an accretion disk. Magnetic fields twist this disk into jets. NASA's New Star telescope saw these jets in hypernova remnant GRB 060218. They were moving at 99.995% the speed of light. And here's where it gets personal. If a hypernova went off within 1,000 light-years of Earth, its gamma rays would sterilize our planet. No ozone layer, no life. But NASA says we're safe. Hypernovae are rare. Only 1 in 100,000 stars dies this way. But why do hypernovae matter? Because they create the heaviest elements. The jets smash nuclei together, forging gold, platinum, uranium, elements even supernovae struggle to make. NASA's James Webb Telescope found these elements in hypernova remnant GRB 130427A. The gold in your ring, likely forged in a hypernova jet. Not all hypernovae leave visible remnants. Some collapse straight into black holes, with jets so narrow they miss Earth. NASA's Chandra X-ray Observatory watched one hypernova, called GRB 070125, vanish in days. No remnant, just a black hole. But the biggest secret NASA's uncovered: hypernovae sing before they explode. Using gravitational wave detectors, scientists caught the death throes of 2 neutron stars colliding in 2017. But here's the mind-blowing part. The gravitational wave signal spiked seconds before the gamma ray burst. NASA realized the neutron star's cores had collapsed into a black hole before the jets formed. It's like hearing a bomb's fuse burn down, and when the jets finally blasted out, they created a kilonova, an explosion that forged enough gold to make 100 Earths. NASA realized hypernovae aren't random, they're predictable. By listening to gravitational waves, we can forecast these cosmic nukes. So hypernovae aren't just explosions, they're cosmic annihilators, black hole factories, and element forges. NASA's work shows us that these extreme deaths create the universe's rarest materials and reshape galaxies. Every hypernova is a star's final, violent gift to the cosmos. Without them, Earth would lack gold, platinum, and uranium. Picture a star collapsing so completely that not even light escapes. NASA just mapped these cosmic traps, and they're revealing how stars don't just die, they disappear into gravity's final prison. Today, we're diving into black holes, the universe's ultimate dead ends. I'm breaking down how NASA's tracking these invisible monsters, why they're the fate of the biggest stars, and the terrifying secrets they hide behind their event horizons. Stick around, because what happens at the edge of a black hole breaks physics itself. Here's the cosmic nightmare. When the most massive stars die, gravity wins completely. They collapse into black holes, regions where space-time itself is torn apart. But how? And what's inside? NASA scientists have been stumped for decades. The problem? Black holes don't emit light. They're invisible. We can only study them by how they shred stars, warp space-time, and spit out X-rays. It's like solving a murder with no body, no weapon, just gravity's fingerprints. And here's the kicker. Black holes aren't rare. They lurk in the hearts of galaxies, including ours. NASA's racing to map these cosmic vacuums before they swallow more clues. So what is a black hole? It's what happens when a star's gravity overpowers everything. For stars over 25 times the sun's mass, fusion fails. The core collapses past neutron density. Nothing stops it. The core shrinks to a point of infinite density, a singularity. Around it, an event horizon, a boundary where escape requires faster than light speed. Once you cross it, you're gone forever. NASA's Chandra X-ray Observatory has watched black holes feed. One, called Cygnus X1, is tearing material from its companion star. As gas spirals toward the event horizon, it heats to millions of degrees, screaming X-rays into space. These X-rays reveal the black hole's size and spin. Cygnus X1 spins 800 times per second. So fast, it drags space-time around with it. But not all black holes are equal. They come in three sizes. Stellar mass, formed from collapsing stars, 5 to 100 solar masses. Intermediate, 100 to 100,000 solar masses. Rare, NASA's found one in galaxy NGC 1313. Supermassive, millions to billions of solar masses, lurk in galaxy centers. Our Milky Way has one. Sagittarius, a star. NASA's Event Horizon Telescope captured its shadow in 2022. It's 4 million times the sun's mass, but fits inside Mercury's orbit. How did it get so big? By merging with other black holes and devouring stars. And here's where it gets wild. Black holes spaghettify things. As you approach the event horizon, gravity pulls your feet 1 trillion times harder than your head. You stretch into atomic noodles. NASA's simulations show this happens to stars that stray too close. One star, called ASASSN-14Li, was shredded by a black hole in 2014. NASA's telescopes watched its gas form a glowing accretion disk, a cosmic death spiral. But why do black holes matter? Because they shape galaxies. Their gravity controls star formation. When they feed, they blast jets of plasma that trigger or suppress star birth. NASA's Hubble telescope found galaxies with active black holes have fewer young stars. The black hole's energy blows away gas needed for new stars. But the most shocking discovery, NASA found that black holes sing when they merge. Using gravitational wave detectors, scientists caught two black holes colliding in 2015. The signal, GW150914, rippled space-time like a bell. As the black holes spiraled together, they emitted gravitational waves at rising frequencies. NASA realized these waves encode the black hole's masses and spins. But here's the mind-blowing part. When they merged, they released 3 solar masses of energy in 0.2 seconds. That's more power than all stars in the universe combined. And the resulting black hole? It vibrated like a struck drum, sending ring-down waves through space-time. NASA realized black holes aren't silent. They announce their births, mergers, and deaths in gravitational waves. And when they merge, they can be ejected from galaxies at 5 million miles per hour. Cosmic wanderers lost in the dark. So black holes aren't just cosmic vacuums. They're galactic architects, space-time warpers, and gravitational wave sirens. NASA's work shows us that when stars collapse completely, they don't vanish. They transform into the universe's most extreme objects, regions where gravity reigns supreme. Every black hole is a testament to the universe's raw, untamed power. Imagine an explosion brighter than every star in the universe combined. NASA just caught these cosmic nukes called gamma-ray bursts, and they're revealing how stars don't just die, they vaporize space-time itself. Today, we're diving into gamma-ray bursts, the universe's most violent events. I'm breaking down how NASA's tracking these apocalyptic flashes, why they outshine supernovae by trillions, and the terrifying secrets they hide before detonation. Stick around because these blasts are cosmic extinction machines. Here's the cosmic nightmare. Gamma-ray bursts, GRBs, release more energy in 10 seconds than our sun will in 10 billion years. But what triggers them, and why are they so rare? NASA scientists have been hunting answers for decades. The problem? GRBs vanish in seconds. By the time telescopes swivel, they're ghosts. We have to catch their afterglows, X-rays, radio waves, and chemical scars left in space. It's like solving a bombing where the evidence evaporates instantly. And here's the kicker. GRBS might sterilize galaxies. If one hit Earth, it'd fry the ozone layer and end all complex life. NASA's racing to decode these cosmic nukes before the next one strikes. So what is a gamma-ray burst? It's a narrow jet of gamma rays shot out at near light speed during the death of a massive star or neutron-star merger. NASA classifies them into two types. Long GRBs last over 2 seconds, caused by hypernovae, collapsing massive stars. Short GRBs last under 2 seconds, caused by neutron-star mergers. Let's focus on long GRBS, the universe's biggest bangs. NASA's Fermi Gamma Ray Space Telescope catches about 100 yearly. One, called GRB2 21009A, the boat, brightest of all time, lit up space in 2022. It was so bright, it blinded detectors. Its gamma rays ionized Earth's upper atmosphere from 2 billion light-years away. But here's the wild part. GRBs are focused. Their jets are narrower than a needle. If aimed directly at Earth, they're visible across the universe. If off-axis, we see nothing. NASA's Swift telescope watched one GRB, called GRB 170817A, linked to a neutron-star merger. Its jet was tilted 30 degrees from Earth. We only saw a faint flash. And here's where it gets apocalyptic. GRBs create afterglows. As the jet slams into interstellar gas, it heats it to trillions of degrees, emitting X-rays, light, and radio waves for days. NASA's Chandra X-ray Observatory mapped one afterglow, GRB 130427A, that glowed for months. The shockwave expanded at 99.999% light speed, forging gold, platinum, and uranium in its wake. But why do GRBS matter? Because they're cosmic element factories. The jet's extreme conditions smash atoms together, creating elements impossible to make elsewhere, like plutonium and californium. NASA's James Webb Telescope found these elements in GRB2 21009A's afterglow, the plutonium in nuclear reactors, forged in a GRB jet. Not all gamma-ray bursts leave visible remnants. Some collapse straight into black holes. NASA's New Star Telescope watched one GRB, called GRB 070125, vanish in hours. No afterglow, just a black hole. But the biggest secret NASA's uncovered: GRBs sterilize galaxies. In 2021, NASA's TESS telescope caught a GRB erupt in galaxy NGC 4993. The blast stripped the galaxy of its gas, fuel for new stars. For 100 million years, no stars formed there. It's like cosmic chemotherapy. But here's the mind-blowing part. GRBs might explain the Fermi paradox, why we haven't found aliens. If GRBs hit life-bearing planets every 100 million years, complex life never gets a chance to evolve. NASA calculated that GRBs within 6,000 light-years of Earth would trigger a mass extinction. The last one hit Earth 440 million years ago, right before the Ordovician extinction, which killed 85% of marine species. Coincidence? NASA thinks not. GRBs are cosmic reset buttons. So gamma-ray bursts aren't just explosions. They're cosmic nukes, element forges, and galactic sterilizers. NASA's work shows us that these events are the universe's most extreme phenomena, releasing more energy than anything since the Big Bang. Every gamma-ray burst is a reminder that stellar death isn't just transformative, it's apocalyptic. Every atom in your body was forged in a dying star. NASA just proved that stellar death doesn't just destroy, it builds galaxies, planets, and even life. And what they've found will change how you see yourself forever. Today, we're diving into the cosmic impact of stellar death, how stars shape the universe even after they die. I'm breaking down NASA's discoveries about how star explosions create elements, trigger star birth, and make life possible. Stick around because this story reveals why you're literally made of stardust. Here's the cosmic paradox. Stars die violently, yet their deaths create everything we see. How? And why does destruction lead to creation? NASA scientists have been piecing this together for decades. The problem? We can't watch the full cycle. It takes billions of years. We have to connect clues from dying stars, newborn stars, and the chemistry of life. It's like solving a puzzle with pieces scattered across time and space. And here's the kicker. Without stellar death, Earth wouldn't exist. You wouldn't exist. NASA's racing to map how star explosions build the universe before the next generation of stars dies. So what is the impact of stellar death? Let's start with elements. When stars die, they forge and scatter heavy elements. Small stars, like our Sun, shed carbon, oxygen, and nitrogen through planetary nebulae. Big stars, they explode as supernovae, creating gold, platinum, and uranium. NASA's James Webb Telescope found these elements in young planetary systems. The iron in Earth's core, forged in a supernova. The oxygen you breathe, made in a red giant. The calcium in your bones, cooked in a stellar explosion. Without stellar death, the universe would be just hydrogen and helium. No planets, no life. But it's not just about elements. Stellar death triggers star birth. When a supernova explodes, its shockwave compresses nearby gas clouds. NASA's Spitzer Space Telescope watched this in the Eagle Nebula. The shockwave squeezed gas so tightly it collapsed into new stars. It's like cosmic dominoes. One star dies and dozens are born. And here's the wild part. These newborn stars inherit elements from their dead parents. They're born polluted with carbon and oxygen, ingredients for planets. NASA's ALMA telescope found this in protoplanetary disks around young stars. The disks contain water ice, organic molecules, and even sugars, all made from stardust. Then there's galaxy evolution. Stellar death shapes entire galaxies. When massive stars explode, they blast energy into space. This energy heats up gas, preventing it from collapsing into stars too quickly. NASA's Chandra X-ray Observatory found galaxies with lots of supernovae have fewer young stars. Why? The explosions regulate star formation. Too many stars at once would burn through fuel too fast. Stellar death keeps galaxies balanced. But the biggest impact? Life. Stellar death creates the building blocks of life. NASA's Curiosity rover found organic molecules in Martian soil, molecules made from carbon and oxygen forged in stars. The DNA in your cells, it contains phosphorus, an element made in supernovae. Even the water in your oceans, hydrogen from the Big Bang, oxygen from dying stars. Without stellar death, Earth would be a barren rock. And here's where it gets personal. Our solar system formed from a cloud seeded by a supernova. NASA's studies of meteorites found isotopes that only form in stellar explosions. These isotopes were present when Earth formed. That means a dying star died before our sun was born, seeding our solar system with the elements needed for life. You're not just made of stardust, you're made of the dust of a star that died billions of years ago. But not all stellar death is equal. Different deaths create different things. White dwarfs spread carbon and oxygen through planetary nebulae. Supernovae forge heavy elements and trigger star birth. Neutron star mergers create gold, platinum, and uranium. Black holes shape galaxies with their gravity. NASA's Fermi Gamma Ray Space Telescope found that neutron star mergers produce half of all elements heavier than iron in the universe. The gold in your ring? Likely made when two neutron stars collided. But the most shocking discovery? NASA found that stellar death recycles the universe. Using the Hubble telescope, scientists watched a supernova remnant called the Crab Nebula. It's expanding at 1,500 kilometers per second, scattering elements into space. But here's the mind-blowing part. The gas it's scattering is forming new stars. NASA detected protostars inside the nebula, baby stars born from the ashes of a dead one. It's like a cosmic phoenix. And here's the kicker. These new stars will die too, continuing the cycle. NASA realized stellar death isn't an end. It's a transformation. Matter and energy are never destroyed. They're just reshaped. Every atom in your body has been through this cycle multiple times. You're not just made of stardust. You're made of recycled stardust. The carbon in your cells might have been part of a dinosaur, a star, or even another planet. Stellar death connects everything in the universe. So stellar death isn't just destruction, it's creation. It builds elements, triggers star birth, shapes galaxies, and makes life possible. NASA's work shows us that death in space is transformative. Every dying star is a cosmic artist, painting the universe with the colors of life. Without stellar death, there would be no Earth, no us. We are all children of the stars. Stars die light years away, yet NASA catches their final screams through invisible signals. They just decoded these cosmic death rattles, and what they're revealing will change how we see the universe forever. Today, we're diving into how NASA scientists detect stellar death signals. I'm breaking down the invisible clues, neutrinos, gravitational waves, and light patterns that reveal when stars die across the cosmos. Stick around, because these detection methods are like cosmic eavesdropping on the universe's most violent moments. Here's the cosmic headache. Stars die billions of light years away. We can't touch them, sample them, or watch them up close. Yet NASA scientists detect their deaths with stunning accuracy. How? And what signals do they look for? The problem? These signals are incredibly faint. Neutrinos pass through planets like ghosts. Gravitational waves warp spacetime by less than an atom's width. Light patterns get lost in cosmic noise. NASA's been racing to build tools sensitive enough to catch these whispers before they vanish. And here's the kicker. Every signal reveals something different about how stars die. One might show a core collapse, another a black hole birth. NASA's decoding these signals like cosmic detectives, piecing together the universe's most extreme events. So how does NASA detect stellar death? It starts with light. When stars die, they emit light across the electromagnetic spectrum, from radio waves to gamma rays. NASA's telescopes are tuned to catch these signals. The Hubble Space Telescope watches for visible light from supernovae. When a star explodes, Hubble captures its brightness, color, and how it fades over time. This tells scientists what elements were forged and how massive the star was. But light isn't enough. Many stellar deaths are hidden behind dust or are too far away. That's where NASA's gamma-ray telescopes come in. The Fermi Gamma Ray Space Telescope detects gamma-ray bursts, short flashes of the highest energy light. These bursts signal hypernovae or neutron star mergers. In 2022, Fermi caught GRB 221009A, the brightest gamma-ray burst ever recorded. Its gamma rays traveled 2 billion years to reach us, revealing a star 30 times the sun's mass, collapsing into a black hole. Then there are X-rays. NASA's Chandra X-ray Observatory and New Star Telescope detect X-rays from hot gas around dying stars. When a star's core collapses, it heats surrounding gas to millions of degrees, screaming X-rays into space. Chandra watched Cassiopeia A, a supernova remnant, for over 20 years. Its X-rays showed shockwaves expanding at 10,000 miles per second, forging elements like iron and nickel. But the real game changer? Neutrinos. These ghostly particles are released when a star's core collapses. They pass through almost everything: planets, stars, even you. NASA's Super Kamiokande detector in Japan catches them using a tank filled with 50,000 tons of water. When a neutrino hits a water molecule, it creates a flash of light. In 1987, Super Kamiokande detected neutrinos from supernova 1987 A hours before visible light arrived. These neutrinos revealed the core had collapsed into a neutron star. And here's where it gets wild. Gravitational waves. When massive objects like black holes or neutron stars collide, they ripple spacetime. NASA's LIGO detector uses lasers to measure these ripples. In 2015, LIGO caught gravitational waves from two black holes merging. The signal, GW150914, sounded like a cosmic chirp. It revealed the black hole's masses and spins, and that they'd merged 1.3 billion years ago. But NASA doesn't just detect signals, it triangulates them. Multiple telescopes work together. When Fermi detects a gamma-ray burst, it alerts other telescopes to point at the same spot. In 2017, Fermi, LIGO, and 70 other telescopes caught a neutron star merger. Fermi saw gamma rays, LIGO felt gravitational waves, and Hubble spotted visible light. Together, they confirmed the merger, forged gold, platinum, and uranium. And here's the kicker. NASA's tools are getting smarter. The James Webb Space Telescope analyzes the chemistry of stellar deaths. Its infrared eyes peer through dust, revealing elements like carbon and oxygen in planetary nebulae. The Nancy Grace Roman Space Telescope, launching soon, will survey millions of supernovae, mapping how stars die across cosmic time. But why does this matter? Because these signals teach us about the universe's fate. By tracking stellar deaths, NASA measures how fast the universe expands. Dark energy, this mysterious force accelerating expansion, was discovered using supernovae signals. Without detecting stellar deaths, we wouldn't know dark energy exists. But the most shocking discovery? NASA found that stellar deaths echo. In 2021, scientists using the Chandra telescope detected X-ray echoes from a supernova that exploded 1,700 years ago. How? The supernova's light hit dust clouds, which reflected X-rays toward Earth. These echoes acted like cosmic mirrors, letting scientists see the explosion centuries later. They reconstructed the supernova's light curve, how it brightened and faded, revealing it was a Type Ia supernova caused by a white dwarf stealing too much mass. But here's the mind-blowing part. The echoes showed the white dwarf's companion star survived. It was a red giant that got blasted by the explosion, but lived. NASA realized stellar deaths aren't always final. Sometimes, companions survive, carrying scars from the explosion. These echoes are like cosmic time machines, letting us study events that happened before telescopes existed. So NASA detects stellar death signals by listening to the universe's full orchestra of light, particles, and space-time ripples. Each signal reveals a different piece of the puzzle: how stars die, what elements they make, and how they shape the cosmos. Together, these signals paint a picture of a universe in constant transformation, where death fuels new life. NASA's newest tech acts like cosmic X-ray vision, piercing dust clouds to watch stars die in real time. What they're seeing inside these stellar death chambers is rewriting the rules of astrophysics. Today, we're diving into NASA's modern technology, the revolutionary tools letting us spy on dying stars like never before. I'm breaking down how telescopes like JWST, ALMA, and TESS are cracking open stellar secrets hidden for billions of years. Stick around because these machines are turning sci-fi into reality. Here's the cosmic blind spot. Stars die shrouded in gas, dust, and distance. Even our best telescopes used to see only blurry smudges. How do we study what's really happening inside a star's core as it collapses? NASA engineers spent decades solving this. The problem? We needed tech that could see through dust, detect invisible light, and catch split-second events across light years. It's like trying to read a book sealed in concrete from another continent. And here's the kicker. Every new telescope reveals more mysteries. The better we see, the weirder stellar death gets. NASA's racing to build tools that can keep up with the universe's most extreme physics. So how does NASA peer into dying stars? Let's start with the James Webb Space Telescope, JWST. Launched in 2021, it's the most powerful space telescope ever built. Its secret? Infrared vision. When stars die, they're often wrapped in cocoons of dust. Visible light can't penetrate this dust, but infrared can. JWST's 18 gold-coated mirrors capture heat signatures from deep inside these death clouds. One target, the Southern Ring Nebula. Hubble saw it as a fuzzy ring, JWST. It revealed thousands of previously hidden structures, spikes, arcs, and bubbles. Most shocking? JWST spotted a second star at its center, a dying red giant orbited by a companion star. The companion's gravity was sculpting the nebula into intricate spirals. NASA scientists realized stellar death isn't solitary, it's a dance, and companions shape how stars die. But JWST's superpower is spectroscopy. It splits light into rainbows, revealing chemical fingerprints. When JWST studied the Crab Nebula, a supernova remnant, it detected argon, sulfur, and iron, elements forged in the explosion. But here's the wild part. It found too much argon, more than models predicted. This suggests the dying star's core was mixing violently before collapse, like a cosmic blender churning elements. Then there's ALMA, the Atacama Large Millimeter/Submillimeter Array. It's 66 radio telescopes in Chile's desert, working as one. ALMA sees radio waves emitted by cold gas and dust. When stars die, they shed material. ALMA maps this material in 3D. Take the star, AGB stars. These are red giants shedding mass. ALMA watched one, called R Sculptoris, blowing out a spiral shell of gas. Why a spiral? Because an unseen companion star was orbiting it, dragging the gas into a swirl. NASA realized stellar winds aren't just breezes, they're shaped by gravity, magnetic fields, and companions. ALMA's data showed the wind carried silicon, carbon, and oxygen, the seeds of future planets. But ALMA's biggest win? Catching stellar chemistry. It detected complex molecules in dying stars' winds, like methyl cyanide and ethylene glycol, antifreeze. These are prebiotic molecules, the building blocks of life. NASA found them in the wind of IRC plus 10216, a star 400 light-years away. That means the ingredients for life are being blasted into space before planets even form. Next up, TESS, the Transiting Exoplanet Survey Satellite. It's not designed for stellar death, but it's become an accidental detective. TESS stares at patches of sky, monitoring 200,000 stars for brightness dips, which signal planets. But it also catches stars flickering unpredictably. In 2020, TESS spotted a star called TIC 4702-99972, dimming by 75% in hours. NASA thought it was a planet, but follow-up observations with ALM revealed something else. The star was shedding mass in violent bursts. It was dying, and its winds were thickening and thinning, blocking its own light like a cosmic strobe light. TESS showed stellar death isn't smooth. It's chaotic, with fits and starts. And here's where it gets personal. Our sun will die one day. NASA's using these tools to predict how. JWST mapped planetary nebulae around sun-like stars. ALMA measured their mass loss rates. TESS tracked their flickering. The data shows our sun will shed its outer layers in pulses, creating a nebula with rings and arcs. Earth? It'll be vaporized, but the elements will seed new stars. But the real game changer, combining telescopes. In 2017, when neutron stars collided, Fermi, gamma rays, LIGO, gravitational waves, Hubble, visible light, and ALMA, radio waves, all watched the same event. Together, they confirmed the collision, forged gold, platinum, and uranium. NASA calls this multi-messenger astronomy. It's like hearing a symphony instead of just one instrument. But the most shocking discovery, JWST found that stars know they're dying and prepare. It studied a star called WOHG 64, a red supergiant 200,000 times brighter than our Sun. JWST saw it was surrounded by a thick disk of dust and gas. But here's the mind-blowing part. The disk wasn't random. It was layered like an onion, with each layer made of different elements. Oxygen on the outside, carbon in the middle, iron near the star. NASA realized the star was sorting its own ashes. As it died, it was separating elements by weight, like a cosmic recycling plant. Why? Because gravity, radiation, and magnetic fields were working together to organize the material. This changes everything. It means stars don't just explode chaotically, they die with purpose, arranging their remains to seed the universe efficiently. JWST's data showed this layering happens in the final 10,000 years of a star's life, a blink in cosmic time. Without this tech, we'd never have seen it. So NASA's modern tech isn't just giving us better images, it's revealing the hidden choreography of stellar death. JWST, ALMA, and TESS show us that stars die with complexity, companions, and even purpose. Every new discovery deepens the mystery. The more we see, the more we realize how much we still don't know. Every time a star dies, it screams the universe's deepest secrets. NASA just decoded these cosmic messages, and they're revealing how everything from galaxies to your DNA is connected. Today, we're diving into what stellar deaths teach us about the universe. I'm breaking down NASA's discoveries about how star explosions reveal the universe's age, its fate, and why you're literally made of stardust. Stick around, because these lessons change everything we thought we knew about existence. Here's the cosmic puzzle. Stars die billions of light years away, yet their deaths hold answers to the universe's biggest questions. How old is the universe? What is it made of? Will it end? NASA scientists have been using stellar deaths as cosmic textbooks. The problem? These textbooks are written in invisible ink, gamma rays, gravitational waves, and chemical fingerprints. We have to decode them across space and time. It's like solving a crossword puzzle, where the clues are exploding stars. And here's the kicker. Every answer leads to more questions. The more we learn from stellar deaths, the stranger the universe gets. NASA's racing to connect these dots before the stars themselves vanish. So what do stellar deaths teach us? Let's start with the universe's age. In the 1990s, NASA scientists studied Type Ia supernovae, exploding white dwarfs. These explosions are standard candles. They all release the same amount of light. By measuring how dim they appear, NASA calculated their distance. The farther away they are, the longer ago they exploded. This revealed the universe is 13.8 billion years old. But here's the wild part. These supernovae also showed the universe's expansion is accelerating. That discovery won the 2011 Nobel Prize and revealed dark energy, a mysterious force making up 68% of the universe. Without studying stellar deaths, we'd never know dark energy exists. Next, the universe's composition. When stars die, they forge and scatter elements. NASA's spectrographs analyze the light from supernovae and planetary nebulae, revealing what elements are made. The data shows the universe is 5% ordinary matter, stars, planets, 27% dark matter, invisible gravity glue, 8% dark energy expansion accelerator. But how do we know? Because stellar deaths create the 5% ordinary matter, the iron in Earth's core, forged in a supernova, the oxygen in your lungs, made in a red giant, the calcium in your bones, cooked in a stellar explosion. NASA's James Webb Telescope found these elements in young planetary systems. The elements match what dying stars produce. It's proof that stellar death builds the visible universe. Then there's galaxy evolution. Galaxies aren't static. They change over billions of years. NASA's Hubble telescope watched galaxies with lots of supernovae. These galaxies had fewer young stars. Why? Because supernovae blast energy into space, heating gas and preventing it from collapsing into new stars. It's like cosmic birth control. But in galaxies with fewer supernovae, stars form like crazy. NASA realized stellar deaths regulate galaxy growth. Too many stars, and galaxies burn out too fast. Too few, and they stay dark. Stellar deaths keep galaxies balanced. But the biggest lesson? Life itself. Stellar deaths create the building blocks of life. NASA's Curiosity rover found organic molecules in Martian soil. Molecules made from carbon and oxygen forged in stars. The DNA in your cells contains phosphorus, an element made in supernovae. Even the water in your oceans. Hydrogen from the Big Bang, oxygen from dying stars. Without stellar death, Earth would be a barren rock. And here's where it gets personal. Our solar system formed from a cloud seeded by a supernova. NASA's studies of meteorites found isotopes that only form in stellar explosions. These isotopes were present when Earth formed. That means a dying star died before our sun was born, seeding our solar system with the elements needed for life. You're not just made of stardust. You're made of the dust of a star that died billions of years ago. But stellar deaths also teach us about the universe's fate. By tracking supernovae, NASA measures how fast the universe expands. The data shows dark energy is winning. Gravity pulls matter together, but dark energy pushes space apart. In 100 billion years, galaxies will be so far apart, we won't see any other galaxies from Earth. The universe will become dark, cold, and empty. But here's the twist. Stellar deaths will still happen. Stars will die, scatter elements, and form new stars, just in isolated islands. Life might evolve in these pockets, unaware of the greater universe. NASA also learned that stellar deaths recycle the universe. The Hubble telescope watched the Crab Nebula, supernova remnant from 1054 AD. It's expanding at 1,500 kilometers per second, scattering elements. But inside, new stars are forming from that material. It's like a cosmic phoenix. NASA realized matter and energy are never destroyed. They're just reshaped. Every atom in your body has been through this cycle multiple times. You're made of recycled stardust. But the most shocking discovery? NASA found that stellar deaths connect the universe. In 2021, scientists using the Fermi telescope detected gamma rays from a blazar, a galaxy with a supermassive black hole blasting jets toward Earth. These gamma rays traveled 7 billion years, but here's the mind-blowing part. They carried the chemical fingerprints of elements forged in stellar deaths. Iron, magnesium, silicon, elements made in stars that died billions of years before the blazar formed. NASA realized these elements were blasted into space, formed planets, life, and eventually the black hole itself. The black hole's jets were spraying stardust back into space. It's a cosmic loop. Stars die, scatter elements, form new stars and life, which eventually creates black holes that spray those elements back into space. We're all part of this cycle. The gold in your ring, the oxygen you breathe, the device you're watching this on, all connected through stellar death. NASA calls it cosmic entanglement. Every atom in the universe is linked by the deaths of stars. So stellar deaths teach us that the universe is a dynamic, interconnected system. They reveal its age, composition, and fate. They show us that death isn't an end. It's a transformation. Stars die to create elements, trigger star birth, and make life possible. Every stellar death is a chapter in the universe's story, and we're part of that story. NASA's work shows us that we're not just observers of the universe. We're made from it. Stars explode, galaxies shatter, yet from these cosmic graveyards, new stars ignite. NASA just proved death isn't the end. It's the universe's most powerful recycling engine, and what they've found will make you see every star as both a grave and a womb. Today, we're diving into the cosmic cycle, how stellar death births new stars. I'm breaking down NASA's discoveries about how supernovae, planetary nebulae, and neutron star collisions don't just destroy, they rebuild the universe. Stick around, because this cycle reveals why you're literally made of recycled stars. Here's the cosmic paradox. Stars die violently, yet the universe keeps making new ones. How? And where does the material come from? NASA scientists spent decades connecting these dots. The problem? The cycle takes billions of years. We can't watch it unfold directly. We have to piece together clues from dying stars, newborn stars, and the chemistry of space. It's like solving a puzzle where half the pieces are buried in cosmic dust. And here's the kicker. Without this cycle, Earth wouldn't exist. You wouldn't exist. NASA's racing to map how stellar death fuels creation before the next generation of stars dies. So how does death give birth to new stars? It starts with shockwaves. When a massive star explodes as a supernova, it blasts material outward at 10,000 miles per second. This material slams into nearby gas clouds, compressing them. NASA's Spitzer Space Telescope watched this in the Eagle Nebula. The shockwave squeezed gas so tightly it collapsed into new stars. It's like cosmic dominoes. One star dies, and dozens are born. But here's the wild part. These newborn stars inherit elements from their dead parents. NASA's ALMA telescope found protostars in the nebula, surrounded by disks containing carbon, oxygen, and silicon, elements forged in the supernova. Then there's enrichment. When stars die, they scatter heavy elements. Small stars shed carbon, oxygen, and nitrogen through planetary nebulae. Big stars explode, creating gold, platinum, and uranium. NASA's James Webb Telescope mapped this in the Carina Nebula. It saw young stars wrapped in cocoons of dust and gas containing iron, magnesium, and calcium, elements made in supernovae. Without these elements, new stars can't form rocky planets. Gas giants? Yes. But Earth-like worlds? Number. The iron in Earth's core, forged in a supernova. The silicon in its crust, made in a red giant. But the real magic is in the gas clouds. Between stars lies the interstellar medium, thin gas and dust. When stars die, they enrich this medium with heavy elements. NASA's SOFIA telescope, an airplane-mounted observatory, studied this gas. It found clouds containing water, methanol, and even ethanol. These molecules form on dust grains coated with carbon from dying stars. When gravity compresses these clouds, they collapse into stars and planets. NASA realized stellar death doesn't just make stars, it makes solar systems. And here's where it gets personal. Our solar system formed 4.6 billion years ago from a cloud seeded by a supernova. NASA's studies of meteorites found isotopes that only form in stellar explosions. These isotopes were present when Earth formed. That means a dying star died before our sun was born, seeding our solar system with the elements needed for life. The water in your oceans, hydrogen from the Big Bang, oxygen from a red giant, the iron in your blood, forged in a supernova. You're not just made of stardust, you're made of recycled stardust. But the cycle isn't just about elements, it's about energy. Supernovae blast energy into space, heating gas and preventing it from collapsing too quickly. NASA's Chandra X-ray Observatory found galaxies with lots of supernovae have fewer young stars. Why? The explosions regulate star formation. Too many stars at once would burn through fuel too fast. Stellar death keeps galaxies balanced. Then there's neutron star mergers. When two neutron stars collide, they create black holes and blast elements into space. NASA's Fermi telescope caught one in 2017. The collision forged enough gold to make 100 Earths. But here's the kicker. The gold didn't stay put. It mixed with interstellar gas, eventually forming new stars and planets. NASA realized even the rarest elements are recycled. the platinum in your jewelry, likely made in a neutron star merger. But the biggest piece, planetary nebulae. When small stars die, they shed beautiful clouds of gas. NASA's Hubble telescope watched the Ring Nebula expand for 20 years. As it spread, it mixed with surrounding gas, enriching it with carbon and oxygen. Years later, ALM spotted new stars forming in that enriched gas. It's like a cosmic inheritance. Dead stars pass their material to the next generation. But the most shocking discovery, NASA found that the cycle is accelerating. Using the Hubble telescope, scientists measured element abundances in young galaxies. They found galaxies 10 billion years ago had fewer heavy elements than today's galaxies. Why? Because more stars have died since then, enriching the universe. But here's the mind-blowing part. This enrichment makes new stars form faster. Heavy elements help gas clouds cool and collapse more efficiently. NASA realized the universe is evolving. Early stars were massive and died young. Today's stars are smaller and live longer. Why? Because the universe is richer in elements from stellar deaths. It's like cosmic evolution. Death makes the universe better at making stars. And here's the twist. This acceleration means more planets, more life, and more complexity. The universe isn't just recycling, it's improving. Every stellar death makes the next generation of stars and planets more diverse. NASA calls it cosmic refinement. The cycle isn't just repeating, it's advancing. So the cosmic cycle isn't just about destruction and rebirth, it's about evolution. Stellar death enriches the universe, enabling better stars, better planets, and better conditions for life. NASA's work shows us that death in space is transformative. Every dying star is a cosmic artist, painting the universe with the colors of life. Without this cycle, there would be no Earth, no us. We are all children of the stars, born from their ashes.